Good morning, everyone. I hope you're all good. We are going to do more of a standard live stream today. Instead of just studying the book, the physically based rendering book, which I actually haven't got open. So if you bear with me for a moment while I get that open. We should... we're going to do also some programming. We also need to do revision. I haven't had the chance to do much revision recently. Let me just grab the chat open. Okay, dokie. So yes, we're actually going to be doing coding later. Who would have thought on a coding stream? What the hell? It's like I'm trying to program something or something like that, you know? Who would have thought? So yeah, we're going to the reason that I obviously there's two competing ideas that I have to deal with. One is this book that I'm studying. I need to get far enough through the book that it's actually useful. Otherwise, it was a giant waste of time, right? I think I've said that a couple of times, but that's important to say at the beginning. So that's why I'm going super hard on this, right? But I also need to balance that with the fact that I need to actually code. Otherwise, you know, I'm going to get rusty, even if it's just a couple of days, right? I can't just, you know, sit here and study theory for the, you know, remainder of the month and expect to immediately know what to do with my engine. So I've got to keep fresh on that. So that's what we're going to be doing afterwards. So it's going to be a 3-part stream. Revision, which, like I said, I need to go over what I've been doing yesterday. I haven't had the chance to do that yet. So we're just going to be going over my notes that I've written and correcting some spelling mistakes, all that kind of stuff that we usually do. Then it will be going into the book itself. Like we did yesterday, we can probably plow through a bit more than we did yesterday because I don't have to learn probability from scratch like I was yesterday and all that kind of stuff. So based on what we did yesterday, we got that foundation, so we'll hopefully be able to go a bit further. And then after that, we'll be able to, you know, code some stuff, get some stuff working that's better. Maybe I'll tackle the physically based renderer's normal mapping problem. Something's wrong with the normals, so we end up kind of lighting things in the wrong direction. So yeah, we can try and tackle that today. And a couple of other things. I'm probably not going to go too deep into anything in particular. I'm probably going to kind of move around, make sure everything's kind of going in the right direction, and, you know, evening out things. So yeah, it's going to be probably physically based rendering, lighting, so shader stuff. And what else should I do? Probably start down the path of removing things from the scene when the collision detection happens. Because right now in our engine, actually I can just show you. This is me messing with this yesterday. We have a problem. Well, we don't have a problem per se. It's, whoops. Oh yes, and this, okay, I forgot about this. This has been an issue all of a sudden. It is not, the swap chain, what is it called? Image buffer thing just isn't allocating memory or something like that. So that's something we're going to tackle as well. So that's a good job I remembered that. So there's small things like that that I need to just update. After that broke after a refactor. So when I collide into a thing, there we go. It makes a noise, right? But I want to be able to start testing the idea of a collision event happening in the physics engine, and then removing things from the scene. So I think what I'm going to try and do is build a stable ID system into the game engine, and refer to that basically once it's collided in like this, and then we can, like, okay, find out what this one is, like this rock here, for example, crash into it, and then remove it without the physics engine spazzing out, which is what's an issue right now. Is the physics engine needs everything to kind of be stable for some reason. So that's what we're going to tackle today in general. So yeah, hopefully you're all here for it, and yeah, it's going to be a bit of a shorter stream, probably like 5 hours instead of 6. Just because I started a bit late. I woke up really late today. I was working all the way up till I went to sleep, and that's not the best idea for sleep. So I ended up sleeping until 7 o'clock, which was pretty late for me. So yeah, so revision-wise, that's why I haven't been able to do revision. So what we're going to do is we're going to kind of read through some of this that we've been kind of studying. We're going to go to the source note, which is what we've been writing, and kind of have to go through some of the probability stuff that we did yesterday. And I keep forgetting this, what this means. Yes, stochastic progressive photonic mapping. So there's things like that that I just need to make sure I go over so I can actually understand more advanced ray tracing that's going to build into our physically based renderer with the BRDF and the BSDF and the BSSDF functions that we might be able to do for our lighting system. So yeah, that's generally what we're going to be doing today. So I hope you're all here for it. Again, for the revision and the reading of the book, I'll be reading it out loud, so it's not just you staring at a empty screen with no audio. So yeah, that's how we're going to be doing it today. So yeah, let's dive into it, and I'll start the timer on development, which is nice. Yeah, I've been loving these times, by the way. 8 hours a day, which is lovely. So yeah, let's see what we can do. Where should we start? We should start with I think I read these yesterday, and I think I should read these today and the stuff. So yeah, the revision's going to take a while. So yes, it's one of those things where I have to accept that the point of writing notes is to reread them at some point. So here we go. Ray object intersections. Okay, the renderer needs, say, a renderer, not the renderer. A renderer needs to figure out if, if, when, and where something is hit from the camera. We are interested in what the ray hits first. This is to get the point at which we need to simulate light. Fantastic. We can use the parametric form of a ray for this. If the R is an array, or is a ray, and D is the direction vector, and O is the origin at which the ray starts. Now let's just kind of finish off the sentence. Then we have this. If we use the T parameter, which goes from 0 to infinity, we travel down any, not array, ray, to find the point given the value t. We can easily find the intersection with a function fx, yeah, that thing. Yeah, let me just turn the music down a little bit. I feel like it's really loud. It's nice, but it's okay. There we go. So hopefully that wasn't too loud. I apologize for that. I just realized like how loud the music was. Anyway, so we substitute the ray equation into the implicit equation and make a function whose only parameter is t. We solve this function for t and substitute the smallest possible root into the array equation to find the point. Hi, Burning Toast. Hi, I was in your stream yesterday. Yes, I remember. And I started using Obsidian, and it's pretty damn good. A mix of Markdown and LaTeX is amazing. Yeah, it's. I'm glad you enjoy it. Yeah, it's. There's a lot of different options out there for note taking, and I generally think that it doesn't matter which one you pick. But I just like the way the Obsidian's laid out. I like the Markdown / LaTeX thing. Yeah, so it's. I'm glad you're enjoying it too. Yeah, it's good to see you. Good to see you too. Again, my Burning Toast. I hope you're having a great day. So yes, we're just doing a bit of revision just to catch up on what I'm doing. Because, like I said earlier, the point of making notes, unfortunately, is to reread them. So here we go. So in the case of our function x, y, and z, the function defines a sphere at the origin like this. Yep. Very standard equation for a sphere. We can throw in our ray, that's how you spell equation, like this. Very nice. This gives us a quadratic equation in T. If there is no real roots, the ray is missed. The ray is missed. The ray missed is probably. It just sounds like the mist, you know. If there are real roots, then we just have to take the smallest positive integer of t to get the intersection point. So imagine the equation above. Can you save your notes on the cloud? Your notes, yes. My notes are on GitHub. If you really want to see my notes, they're publicly. I think they're publicly available on GitHub. I don't. Not that it's useful, but yes, that's what I do. I store them on the cloud. But you can also store them on. Excuse me. Let's see if they're actually on GitHub publicly. I don't, because I don't think anyone would actually care. Is this public? I don't know how to tell. But yes, this is what I do. I just stick them on GitHub and do push and pulls and stuff like that. So yes, but if you have a cloud account, just put what you need to do is just put the notes where all your notes are in a place where it can be you know, like let's just say you have a Google Drive, just stick this folder in the Google Drive itself along with the .obsidian and everything should sync. I can steal them, lol. Yeah, that's it. I don't even know. I would have to. How'd you? Actually, you know, it's a really easy check is to see. It's a bit of a procrastination, but if I try, I always forget which. There's too many settings. Yes. Yeah, GitHub's telling me about. Oh yeah, it's public. Yeah, right there. It says right there, public. So in theory, yes, you could steal all my notes. There we go. But yeah, let's crack on. This gives us a quadratic equation. Yep. If they are real roots, then take the smallest positive integer intersection point. So imagine that you had an equation. Now cast the ray with this over the quadratic, and we do this until we have a real root while increasing t over time. Once we have a real root, we have an intersection. Yes, I think now I remember why I made them public. I made them public because I wanted to have them at work, and I think it was a bit more. They agreed that I could pull a repository if it was public. Because they were a bit, you know, you've got to be careful with like copyright and stuff. So if it was publicly available, then technically it was fine for them. But I would assume that it's not that useful for anyone to actually look at my notes particularly. But anyway, but yeah, feel free to use them if you actually need them. I should actually push this up. I haven't pushed this up in a month. Anyway, just doing ray intersection for a given ray. I meant to say here, ray is not enough. We need to pass the properties of a given surface to the next part of the ray tracing algorithm to shade the point. I know is shade has got an e. To shade the point, we need to pass. To shade the point, we need to pass the geometric information as well. We always need to pass the surface normal, which actually is normal. Yep. Okay. So I'll assume that hat is normalized to the later part of the algorithm. We need to worry about partial derivatives of position and surface normals with respect to local parameters of the surface. If we can, comma, to be more accurate. However, you can just pass the normal for a simpler ray tracer. Simple implies that it's bad, but I think if I was to have a ray tracer without RT hardware, I think I would just pass the normal, just so there's less data. Okay, so the general approach to ray tracing. The brute force approach would be to pass rays out of each object in a scene until we are done. This is extremely slow for offline, this is extremely slow even for offline ray tracers. A better approach is to incorporate acceleration structures to quickly reject a whole bunch of objects from ray intersection testing. If you implement this correctly, your time complexity is OM log n, where m is the number of pixels and n is the number of number of objects. Sorry. There we go. You see the benefit of this, that we can break up the topics into little bits, so it's a lot easier to digest. Yeah, simple implies bad, which is not true. Yeah. Yeah. Yeah, have to quote me on that in the future when I'm cancelled. That's why. I said simple is bad. Okay, light distribution. Okay, light distribution. The ray object intersection. When it comes to ray tracing, it gives us a point and info of the geometry. When it comes to... Oh, when it comes... Yeah. Sorry. Let me rearrange this sentence a little bit. It's a little bit clumsy. Right. When it comes to object ray intersection, for ray tracing, it gives us a point and the geometric information. We need to figure out, in addition to that, how much light is hitting that scene. Oh yeah, this is the power. This is done both with the geometry and the radiometric distribution of light. Very nice. So, for something like a point light, geometric distribution of light is simply knowing the position. This isn't found in real life. To match reality, we have to use area-based lighting. Nice. We need to worry about the amount of light power being deposited on a differential area surrounding the intersection point P. We will talk about point lights to drill the basic concepts. This picture gives the general idea. Okay. We will assume that the point light has some... Oops. Ooh. I dropped my water bottle on the floor. Has some power associated, has some phi associated with it, and it radiates light equally in all directions. This means that the power per area on a unit sphere surrounding the light is phi divided by 4 pi. We based on the area, which is based on the area of a sphere, because that's actually where that comes from. If we have a sphere that accounts for the power that gets larger and further away from the point light, we lose power at a rate of 1 over radius squared. This is the inverse square law. If we are interested in working out the power that's distributed. Let's type that out. Distributed. I just type it out again. Is that not correct? Quick. Typing out things. There we go. Let's distribute it on a patch of surface, and we will on a patch of surface, and we tilt that patch of surface by theta from the vector from the surface of that point light. The distribution of power, the area, is proportional to cosine of theta. Putting that all together, you get the differential radians equation, which is very nice. It's quite important, this one. This is for any type of light source. You have, let's put an E there. The two laws in this equation, cosine fall off of light and the tilted surface, and the 1 over r squared fall off of light with distance. Yes. Okay. Good stuff. Okay. The theory of handling more than one light. Illumination is linear, so you can can easily add more than, oh dear, one light source. You compute the lights separately and sum them all to obtain the contribution of light. You can randomly sample light with a good algorithm using only some of the light sources for each shaded point in the scene because of this light linearity with ray tracing. There we go. Next, light linearity. Light visibility, sorry. With ray tracing, it is easy to figure out if the light is casting shadows from the point it is being shaded. We basically go in reverse for a given light source. We take a point on a surface and travel towards the light. These are called shadow rays. S. Put that on there. This works exactly the same way as the ray object intersections, but when we hit something, we have a shadow rather than something we need to distribute power to. If there is no blocking object, the light contributes to the surface. Fantastic. Makes it. It's good to know that because I was starting to forget what shadow rays were. Okay, so light scattered at a surface is probably correct. A surface. Okay, with ray object intersect with a ray object intersection found and the light distribution worked out and the light visibility of the surface worked out for all lights, we can work out the location and incident lighting. We need to work out how much light is scattered back down the ray to the camera. This is the incident light effect. The instant of light arriving along the casted ray, need to add that. Looks like this. So we go cast ray, bing, and then it comes back again. Div. Where omega I interacts with the surface of P and scatters back towards the camera direction at omega origin, or O. The amount, just one M for that word, the amount of light scattered towards the camera is given by the product of the incident light energy and the BRDF. Right, so this is the other part of the light transport equation, which we haven't touched on yet. Oh, okay, so this is, don't know why this didn't correct at a, so when it's dark gray, it's not connecting. Right, okay, so light indirect light transport for rays. Okay, so the indirect light transport for rays, the recursive nature of ray tracing allows for indirect specular reflections. We do this by reflecting a ray. We do this by reflecting a ray at, not a, or at a surface normal at the intersection point if it's shiny. This can happen recursively, which all gets added back to the camera by following back the camera's rays eventually. Next, okay. With hardware-based ray tracing, you can specify a limit, not just limit, a limit to the amount of recursion you have in your pipeline setup. In Vulkan, it's under the max pipeline ray recursion depth. If you do this in a compute shader, you'll need to maintain your own stack for recursion. Okay, so obviously, as you probably know, as programmers who are watching this, recursion needs a stack to operate on, to be pushed and popped on. So this is manually setting up the max amount of the stack that can be used for a recursive ray bounce. But if you're just using a compute shader, you need to maintain your own stack. Even if you just use recursion, this is just for someone who doesn't know. In your language, let's just say, even if you're using Python, you can use recursion. You're using the program stack instead of making your own stack. So yeah, you always have a stack with recursion, no matter what you do. And it can be an optimization, by the way, if you don't know, to create your own stack and use recursion on that stack rather than the program stack, because the program stack's a lot more complicated than just, you know, a chunk of memory that gets pushed and popped on. And anyway, what is stochastic progressive photonic mapping? Since 1980, we've been able to use the recursive nature of ray tracing with indirect transport, the indirect light transport. This really needs to be equation. No, I'll just leave it. But with stochastic progressive photonic mapping algorithms, you are able to accurately simulate simulate the focusing of light that passes through glass. Here we aren't using the stochastic progressive photonic mapping. You can see the shadows are all black. Here we have glass accurately rendered. So yeah, it's all this down here. So will your engine have PBR textures? Yes, they currently do have physically based rendering or physically accurate textures. I just need to accurately simulate that for both rendering techniques and maybe ray tracing techniques. And that requires a bit of knowledge when it comes to how light works, so that's why we're doing this. So yeah, I'm using GLTF models, which supports physically based rendering natively. And if anyone is making their own game engine, is just starting out, that might be an option if you're interested in physically based rendering, to use GLTF models, because they're natively come out the box with roughness and metallic textures and all that kind of stuff that you can start to use for your lighting. Okay, so ray propagation. When working with rays, you have to be aware that you're not always passing through a vacuum, meaning that the surface like the surface like a sphere. Meaning that the surface, like a sphere, will not always equally distribute power across the surface. You have all sorts of effects that include the Earth's atmosphere, causing objects that are further away to appear less saturated. There are two mediums you have to worry about when it comes to ray tracing: and extinguish slash attune. Well, how do you say this word? This is I know the concept, but I need to remember.
Attenuate.
Attenuate. It's not attenuate. It's attenuate. Extinguish and attenuate light, either getting absorbed or scattered. We capture this effect by computing the transmittance of TR between the origin and the intersection point. When we talk about transmittance, we are talking about how much light is scattered at the intersection. Let's say intersection point, not interaction point. Going back to the intersection point. I think camera is what I meant to say. In general, you have stuff like flames that emit light and things that scatter light through a volume, like clouds, or I'd say mist. You have something called volume transport equation, which is used in the same way when we are working out the amount of light that is reflected from a surface with the light transport equation. Very nice. I should be on my Discord server. I made that mistake of not being in my Discord server once, and that was the time that I crashed the graphics card and proceeded to live stream to no one for 2 hours straight. As people in the Discord were trying to tell me the live stream went down. Okay, so introduction to Monte Carlo. Yeah, it is what it is. Yeah, I've got to be careful with it's GPU programming for you. It happens. When solving rendering equations like the light transport equation, we need a method to go about solving these integrals that can be in higher That can be that can be high dimensional. And and discontinuous. Other methods to solve the integrals break down in this case, but the Monte Carlo approach scales nicely with any type of integral that we are interested in solving when rendering. Okay. What this means is that we need to solve for fx for a given integrand with Monte Carlo with a random value. This gives us an estimate, estimated value, yeah, on a given integral. When using randomness in an algorithm, you have two types of categories: Las Vegas and Monte Carlo. I still can't get over why we have a category of algorithms called Las Vegas algorithms. Absolutely no idea why that's the case. Las Vegas algorithms are those that use randomness but give the same result. For example, the entry pivot point in quicksort. The result here being that the array is sorted no matter the value picked. Monte Carlo happens when the randomness used, Monte Carlo happens when you say the Monte Carlo category. We categorize I say Monte Carlo algorithms. Algorithms are when you use randomness, there we go, and you get different results each time, which eventually converges to the correct result. On average, when we rerun the Monte Carlo more than once on the same input. Okay, so basics of CPU ray tracing. Basics of CPU ray tracing. You can't analytically solve the light transport equation, so to do numerically, which is definitely not right. Let's get that right. Thank you. Oops. There we go. So to do numerically, numerically solve this integration to figure out how much light is hitting the camera, you can do something like a basic Monte Carlo. We just randomly select a series of points and we fire rays at them from the camera, following the ray through the scene if it comes back and how it changed. Okay. Even this is actually just the general idea in general. So, so I think I'm gonna rename this. Even if you have something close to 8,192 samples per pixel, because we are randomly selecting points, you'll get a ton of noise plus the most full stop. Plus the most basic approach. You won't handle perfectly specular surfaces. Okay, plus with the most basic approach, you won't handle perfectly specular surfaces. They will always be black. The glass on the table should be specularly lit, not black. So yeah, that's ray tracing being very noisy. Okay, so what I'm going to name this to is how basic ray tracing works. I think that's more accurate for this. Hopefully that updates everything. Yeah. Okay. Cool. Breaking down the light transport equation. Okay, so this is a bit of a meaty one. Here we are breaking down the light transport equation to make it accurately possible to compute. We are going to use random sampling, and return results for both of the light transport equation. Here we are using BSDF, not BRDF functions. BSDF, okay. It is possible with the first part, the emission radiance function of the equation, for a given ray, that the ray itself might not hit anything. However, I'm going to highlight that. That's actually quite useful to remember. Control B. Might not hit anything. However, the global light source that lights up everything has no geometry to be hit, meaning that we need to add light to the scene via this ray based on an infinite light source. Yeah, so that's like, I think, ambient lighting. Okay, so the second part, this integral, has a lot more going on. So now we need to use a random direction vector, omega. Okay, so that needs to be changed from the hat to vec. Let me just fix that. Vec. And where's the other one? I just saw it earlier. No, it doesn't matter. By selecting a random direction, omega prime, we have equal probability over all possible directions. After that, we can estimate the integral. We can estimate the integral. And we can compute. And we can compute the weighted product of the BSDF, which describes the light scattering properties of the material of point P. The light incident spectral, so that is for the diffuse part of the light. So that would be, so when we talk about light scattering, that's diffuse light, meaning that anything that isn't shiny, that reflects light, right? So we have to figure out like how the light source scatters when it hits something that's rough, like matte surface. That would be like the most scattered light. That would be like no reflection at all. And to something that's almost completely reflective, not just basically anything that isn't a perfect mirror, would be going over this BSDF. And this incident of spectral radiance is the shiny part. So that figures out. So we have a roughness versus metallicness when it comes to PBR, and the BSDF or the BSSDF or the BRDF, whatever you want to use, works out the diffuse, and this spectral part works out how metal something is for the roughness and roughness and metal textures that are found in something like the GLTF model format, respectively. So if that's why it's good to have that model format, so you can do both the diffuse, the how light scatters, and the metalness, the spectral, which is how light gets reflected. based on those two texture types. So yeah, highly recommend that if you're interested in physically accurate lighting. Anyway, the spectral, the incident spectral radiance, and the cosine factor for the angle of the surface at P. Okay, so in other words, and by the way, you don't have to do ray tracing for physically based rendering. There is part of the reason I'm reading this book is to not do the ray tracing approach, but because this book is ray tracing focused, I have to do the ray tracing focused stuff to then really dive into how the lighting works for rasterizing, for raster graphics as well as ray tracing graphics. Because if you are doing ray tracing, you're not rasterizing anything, which is good to know. Anyway, in other words, you randomly get the direction of omega prime. Estimating the value of the integral requires evaluating the terms in the integrand for the direction, which is missing an I. Then scale that by 4 pi. And the reason we do this is because we're selecting random points over the unit sphere. So that's why we need to scale it. And for those who don't know, the integrand is just everything after the integral and before the differential part in an integral. So that would be all this here. This fp, blah blah blah, all the way to the cosine. I think. Yeah, because we're doing the integral over a direction vector of. So yeah, it's all this stuff. Since we consider one random direction, there are errors in the Monte Carlo approach compared to the true integral. This is the reason we take multiple samples per pixel, because an average will get a mostly correct result. The BSDF and the cosine leaving us say solving. So later on today, when we actually start looking at my shaders, I'll be looking at the BRDF. I haven't done BSDF. BSDF is more complicated, but I think there's something wrong with my BRDF calculation. So that's what we'll be looking at later on today. Solving the BSDF of the physically based renderer. So solving the BSDF and the cosine angle leaves us with the leaves us with the incident spectral radiance. Let's type function to work out. To work this out, we actually have to run the same process again at the origin point at where the incident spectral radiance, which I'll just kind of highlight these over and over again because they're kind of really useful, is the recursive repeats the process until we hit a certain depth of recursion. So this is what we talked about before when I was talking about recursion at stack. This is to work out how much of the light gets reflected around. And we also, when we bounce light around, we also have to make sure that we decrease the power as light bounces around, because we have the word that I can't remember again. No, what is it? Yes.
Attenuate.
Attenuate. So the light beam attenuates as it travels through non-vacuum space. But you can do vacuum space for the most part. Anyway, to work out the bidirectional surface distribution function, the BSDF, this function is working out how much light is scattered is returning. how much light, working out how much light that is scattered returns S to our camera. We need to get the textures and the surface properties from this for this to work. If the BSDF returns 0, that means that we have a non-transmissive surface, meaning that the surface does not scatter light at all, because the transmissive allows light to pass through it. So this would be a completely black thing, right? Like a black hole, you know. No light is getting out of that. With the absolute cosine theta prime angle and the surface normal, we compute the absolute dot product, which returns the absolute value of the dot product between two vectors. This is because if you take two vectors, dot them together, you get not normalized, the length of these two vectors multiplied together times by the cosine, so that's what they equal. That's why we care about the surface normal. If the vectors are normalized, then it should simplify to this, which is just two normalized vectors equals cosine between the angle between those two vectors. Finally, and it's always the smallest angle, so yeah, you have to be aware of that. So, you know, if you have, I'll explain this for most people who are, what am I getting calculator open for? This is mostly for me, but, you know, if anyone who's watching who's wondering, it's kind of nice to know these type of things. So if I have a vector this way, right, it goes off in this direction. Ignore that dot there. And I have another vector. Oops. You stay red. No, please stay red. Okay. And I have another vector like this. That equality that I just explained is always the smallest angle between, so it's this. That is theta there, right? Is equal to the dot product of both. So if A and B are both vectors, then that is equal to A dot B, assuming that these are normalized, is equal to, I'll just do the length of A times by the length of B, because these aren't normalized vectors, cos theta. The reason I brought this up is because it's never this. It's never this. It's never this. It's never this angle. That's never the case. Anyway, for anyone who's watching, there you go. What time is it for? What a time for this to be recommended? I'm doing the exact same thing. Yo, nice. That's really sick. I'm glad you can join us. And hopefully we can reinforce some topics, maybe together. Maybe you can catch some of my mistakes. There we go. Okay, finally, we generate new rays from the intersection point at the position of omega prime, offset enough that the floating point precision isn't enough. Oh yeah. This is to avoid a second collision at the same point, the same object again. Doing this with recursion completes the approximated function. Hell yeah, we did it. Okay, so we are the shortcoming of so I'm just going over notes right now, but later on we'll be studying a bit of a book that's going to teach us how to do lighting better. Just so you're aware what's going on with this, what I'm reading and why I'm reading this. The shortcoming of the Monte Carlo approach for ray tracing. It's kind of four. Following this method of breaking down the light transport equation, we have a valid ray tracing. We have valid ray tracing, but with many shortcomings. One issue is if the emissive surface are small, which is just aka tiny lights, the rays will often miss them. For example, if you add a point light, for example, you'll get perfect darkness because there is a 0 probability that the ray hits that light. If you have bidirectional scattering distribution function, if the incident light along a direction is high, the random direction vector will often miss it completely, and with perfect mirrors, it's so the more speculative something, the more likely to miss something with this approach. If you want to improve the Monte Carlo process, you can get things more accurate by accurately. However, they are all going to build off the basic idea that we did with breaking down the light transport equation. Nice, Elias. Okay, so final few things I'll read. So samples per pixel. Yeah, you sample more per pixel with ray tracing to average out the results with which increases accuracy. No, that's how you read it. If you have a low amount of random sampling from an algorithm, full stop, the amount of samples with a low amount of samples per pixel. Let's rewrite this a bit. You will get a grainy image because of all the errors. With a low amount of samples per pixel, you will get a grainy image. Get rid of the is because of all the errors. Okay. And next is adding weights to rays. It is possible when dealing with rays that come back in the direction we care about with the... I don't think that's correct. That's the wrong function. That would be for incident spectral radiance. That's the wrong function. That's the spectralness. That we are talking about the first one, which is the emission radiance function, not the specular radiance function. Because we're talking about how much light is hitting the camera, as far as I can tell. Okay, so I come back to the camera, care about the emitted radiance function. We can add weights to the rays which tell the image how much an individual ray contributes to an image. You can, for example, create a vignette, which is a camera effect based on things getting darker towards the edges of the lens. Very nice. Okay, so we did that. We just need to do what is the light transport equation. What is the light transport equation? The amount of light that reaches the camera from a point is given by the sum of light emitted by an object and a light source, and the amount of light reflected. This idea is formalized in the light transport equation, aka the rendering equation. Bum bum bum. This is what you're trying to solve when you're rendering. No matter what you're doing, you're always trying to solve the rendering equation. This means, well, I mean, technically you can just not use a physically accurate renderer. So technically you can use like Blinn Phong or Phong lighting, which is not accurate, but still, it's actually faster for lighting. But you can still use. It's funny with ray tracing and the Monte Carlo approach that ray tracing is, of just randomly selecting values over like a hemisphere over a particular point of a pixel. You can just do instead of the BSDF or the BRDF, you can literally just do a Blinn Phong or Phong lighting, which is kind of funny. So you could do ray tracing and not get accurate results if you want to. This will be more performant though, so it's not necessarily like a bad thing to do. Take it case by case. Anyway, this measures S light with respect to radiance, a radiometric unit. The output of the equation is which states that the point from point P and the direction, this should be a vector. It should be labeled as a vector at least. Vec. And the direction is admitted radiance at a point of direction, which is the admitted light radiance function. Which I'll throw that in there. Which is the fold emitted light radiance function. Okay. Next we do this over all the incident radiance, aka the scattering, from all directions over the sphere. No, sorry, this is the incident radiance is the light coming in over a hemisphere, over a particular point, from all directions over a sphere, hemisphere, I should say. From point, because it is half. A sphere from point P, scaled by the BRDF. Yep, and the cosine term. Fantastic. Okay. You can't solve this analytically, apart from the most simplest of scenes. I would love to see someone write a renderer that solves things analytically. I don't know what that would look like, and what you can even render with that. You either must simplify the assumptions or use numerical integration. Numerican. It's like a. I was born in America. Numerical integration techniques. Weighted ray tracing algorithms simplifies this integral by incoming light from all directions by only in Am I getting this wrong? Hang on. Only from most directions, only in the light radiance, instant radiance. I'll put this in brackets, I guess. Light incident radiance. Oh, I think I understand. Yeah, I got it wrong earlier. Let me correct some of my notes. For directions to the light source. So, yes, that is true that we will get light that scatters off, but if it never hits the camera, then we don't care. So we actually need that kind of reflectance coming back. And if there is no reflectance, then everything's black. So if there's no light that comes back into the camera, then everything's black. Okay, so yeah, if I go back to a note, so I made a mistake in correcting something that was wrong. And it is definitely, yeah, so emitted radiance at the point, yeah, okay. For the direction of light source, it is confusing, the two different functions. Yeah, because the ray tracing algorithm is really interested in this LI function, light incident radiance function. Anyway, for the direction to light source and directions of perfect reflections and refractions. In short, this turns the integral into a small sum over a small number of directions. Yeah, so that simplifies everything down. You can randomly sample, but that's very slow, and you'll need to improve your algorithms to speed it up. Speed it up. Right. Okay, so the next part of the revision I'm going to have to do, unfortunately. Yes, there is more. But to understand this properly, I'm going to have to go over the review of probability, because it is a bit of a hairy, and so we need to do the variance of Monte Carlo, so estimating the accurately. We need to reduce the errors in the Monte Carlo, so we need to review that, and we need to introduce the idea of the Monte Carlo estimator. Then we need to figure out the how the derivative properties work for estimated values and expected values, not estimated. And then we need to figure out basically all the probability distribution functions, which would be the probability mass function, the probability density function, and how continuous ranges work, and the difference between continuous and discrete, dependent and independent values, all that stuff. So yes, we're going to have to review this, because if I don't, I will start to forget it. The most important day to review your notes is the day after you've read them. After you've created them, after a good night's sleep. Otherwise, you'll start to forget. If you learn something, the forget curve when you're studying something is 90% if you never review it after 1 week. So you'll forget 90% of what you've studied and retain 10. Anyway, if you don't do any reviews. Background probability review. In probability, it is common to use a capital X for random values, with the exception of a few Greek letters that mark out special random numbers. Random numbers S are always picked from a domain, and these domains can either be discrete, a finite set, or continuous, all real numbers. For example, when you use a function f with a random number f, this will result in a new random number y. So random number f in function f equals y, which is the whole point of the Monte Carlo system. So when rolling a dice, you are selecting from a set of numbers randomly. Nice. Which would be xi in 1, 2, 3, 4, 5, 6. Each has the probability of 1 over 6, and the sum is always 1, which is important to note. If a random number for probability has an equal chance, we say that it's uniform. That's a uniform. If the probability has an equal chance, we say that that's a uniform what? Variable or function? Let's see, value. That's uniform. I think that's a uniform kind of. That's uniform. Okay. That's. I think that's what I meant to say. If we have a function px that gives us a discrete random that gives discrete random variable. If we have px that gives discrete random variables probability, discrete random variables probabilities. If we have a function x that gives us discrete random number variable probability, this is called a this is called the PMF, the probability mass function. And we also write, and so we can write this as px equals 1 over 6 in this case. You can, sorry, wrong can needs to be here, can have joint, just highlight that, joint probabilities of pxy of two random variables which don't depend on each other. You can work out the probability as a product of two functions s. Okay, so if we have a dependent random variable, if we are randomly picking for example, say if we are picking out marbles from a bag, these marbles are and these marbles are colored differently. Picking one out affects the probability of for picking out another. In this case, the joint probability, we have two marbles of x and y, is a conditional probability. Is of x and y is a conditional probability of y. Oh, yeah, sorry. Okay, I think I'm going to do full stop there, and then say the conditional probability of y is given by is given a value of x, written as px bar y. Okay. This situation, capital letters, is where a variable x is conditional on random values. Sure. We have an import. We have, this is super, like, this confused me like yesterday. It's so silly. But this is literally just RNG. Like, literally, when you talk about like a random number generator, this is literally what it talks about. But in maths, it's defined really strangely. You have an important random variable called the canonical uniform random variable, written as xi, or xi, yeah, xi. This value takes on all values in the domain of 0 to not including 1, independently and with uniform probability. This xi is just RNG in software. We need this for two reasons. First, it is trivial to get this value in software. Hello! Torture again, huh? Yeah, pretty much. But we're going to be coding later on, Dimitri. Thank you for joining us, by the way. Yeah. So hopefully we'll have a bit of fun with what we've learnt. I tested flat buffers, mini reflection C++. So far, I've managed to draw a checkered board and a couple of values on the screen with shapes. Oh, I've not heard of flat buffers. Is that some like middleware thing that allows you to draw extra shapes, kind of like SDL or something, like SDL's renderer? It sounds pretty cool. Oh, I do need to plug in my before I continue. I just realized my laptop is dying. This is a code generator for C++ structures. Oh, okay. I tested flat buffers mini reflections. Okay. Oops. Excuse me. There we go. I'm in a bit of a scuff setup, so there we go. Fantastic. Sounds fun. Generated code, eh? I haven't heard generated code generate C++ code since I worked with Qt, with its Qt generated code stuff. Anyway. Okay. We also need to take a random value from xi that gets the xi, giving us the maths notation. Basically, that just tells us this, right? Domain over that. It's really unnecessarily complicated, but it is what it is for maths. Mathematicians probably like this notation a lot. To write an image, to write an enum generate its string. Yes, I also worked with Qt mock. Is a bit smelly. Yeah, it's yeah, I have horror stories of people messing around with the generated code. Oh my goodness. Someone in our project left the company. This is a horror story, and they took generated code out of the generated code folder called generated in Qt and stuck it in the main source tree. And this was the most confusing thing because they left all the comments in at the top saying, this is generated code, do not modify. And the thing is, he had modified it. So we were trying to fix this by using the Qt designer. But nothing was updating. And it took me like a week to figure out, oh wait, this is just a weird hacked together UI generated code file. It was horrible. Where's your Discord? I'll send you a sample. There are many samples on Google. Yeah, I will give you a link to my Discord. I know you joined earlier, but let me... Feel free to post this in... You can send it to in my DMs, I don't mind, or in the Discord. There's it would be interesting to see. There you go. Anyone's welcome to join, by the way, with that link, if you haven't already. They're there from my wife's account. I see. It needs to be from a normal one. No problem, no problem. Yeah, so there you go. Yeah, yeah. Anyone, like I said, anyone can join. Just follow the rules. That's all you have to do. And then you can have a chill time talking to people about programming, which is what we mostly do. Anyway, so we might MIT MIGHT. For example, want to sample the illumination from each light in the scenes, so its power, phi I, is relative to the entire scene. This sum, SUM, of all the lights will add up to 1. Remember the light linearity thing we talked about earlier? Light is linear, so we can add up everything together. Which, if we add all the lights, it will be equal to 1. Okay, so the commutative distribution function, which is one of the things that confused me yesterday. Px of a random variable is the probability that a value from the variable's distribution is less than or equal to the value of x. So literally, what this function is telling us is this. This alone. This is a complicated name for a less than or equal to operation. Okay, so in the dice example, this would be for P2 equals 1/3, because out of the 6 probabilities, 1 or 2 are less than or equal to 2, meaning that we have a 1/3 chance of that happening. Okay, continuous random variables can be distributed over non-uniform I said continuous random variables. Let's just make sure that's correct. That's obviously spelled wrong. Attenuate, right? Just make sure I get this right. Attenuate. Okay, just making sure. Okay, yeah, continuous random variables. Not what I said. I've half written. Okay, so continuous random variables can also be distributed over non-uniform domains. Anyway, when we have a set like 1, 2, 3, 4, 5, 6, the constant value we are talking about, constant value is equal to the probability distribution function. So this is the thing I need to kind of clean up. The probability mass function, and it's meaning that when we take the integral over the probability of us taking a random number of we are asking what is the probability of the selection of any of these numbers all added together. This is also true for all infinite sets. For infinite sets, we use the continuous extension of sum, aka the integral. Okay, so the probability density function, which describes the relative probability of a random variable taking a particular value is a continuous analog of the probability mass function. The probability density function is the derivative of the random variables commutative distribution function. So the commutative distribution function is defined by the integral over the probability of the over the probability density function. If we integrate over a subsection of the probability density function, we will get a value less than 1. Think about it like this. This with the set random number 1, 2, 3, 4, 5, 6 is a uniform distribution in this uniform distribution of selecting numbers out of a set. If we integrate over and up to the value of 2, then the commutative distribution function is 1/3. If we integrate over the whole uniform distribution, we will, no, let's just say the CDF, what the heck? Oh, I pressed control. The bold CDF will be 1. Right. Yes, I have to explain this extra because otherwise it's super confusing, these connected ideas. Anyway, so let's write down the that down mathematically. So the chances of a value falling within the range of a given value over a probability density function is written as this. This follows the fundamental theorem of calculus. Finally, the probability mass function and the probability density function are the same. The latter is for discrete values like 1, 2, 3, and the other is for continuous values like the real values over, let's just say all the real values over the domain of this. Okay, expected values. The expected value of EP, the expected value, E function, whatever, of a function is defined by the average value of a function over the distribution, over a distribution of values Px over its domain D. So it's just this integral, which is the expected value. This is important to memorize because we actually use this integral later to estimate how accurate Monte Carlos are. Or Monte Carlo estimators, I guess I should say, when it comes to like their convergence. So we are trying to find the expected value of cosine. So if we are trying to find the expected value of the cosine function between 0 and pi, where p is a uniform, the probability density function, because the probability density function must integrate over 1 over the whole domain, we get px equals 1 over pi. And then this whole bit of maths, which I'll explain. So this is the graph. This is because if we add all, sorry, you must integrate over 1. So this is because if we add all the value, this is because if we add, remember we're trying to get the expected value. This is because if we add all the, we add up the average of all these values, which go from -1, which is here, to +1, the average will be 0. So this is why this is equal to 0. Because if you think about it, -1 and 1, the average of these all added together would be 0. It's so hard to live. Everything is blocked. The spoofer, the 3 proxies, and the paid VPN are dead. Oh, that sucks. My sample won't upload to Discord. Should I split it into 2 screens and upload it as text? Yeah, you can do that. Upload it as a text file. If you're really struggling, you can just send it as images. Dimitri, sorry, I don't know if I didn't catch your messages. Just locked in on explaining to myself all this stuff. Yeah, so feel free to, find a way to finagle it in any way that's appropriate. Okay, so right, where are we? So this is because so this is true because of a derivative property of scalars. As the expected value is a scalar, then this hopefully should help you understand what happens below. If we take the sum of all the expected values of a function and pass it in of a function that passes in random variables, that's the same as doing all this. That's the same as adding all the values of that function and getting the expected value from that. So it's just like the sum of the expected values is the same as the adding all the expected values together. Now we can figure out the Monte Carlo estimator. We can now define the Monte Carlo estimator as something that approximates the value of an arbitrary interval over the domain of AB, where the random value is contained in the random variable is within the domain of AB. So the Fn is equal to the integral. So Fn is equal to the integral. This is for a one-dimensional integral. Let's see. Looks like you're able to figure it out. The Dimitri, well done. Thank you for giving us that in this source. Well, I'll let you type out. It looks like you're still typing on the Discord. Anyway, right. So if we consider the whole range of the domain, we can do some algebraic manipulation. We also need to make sure that we understand the probability density function corresponding to the random variables of x must be equal to is that the right way around? I think that's wrong. I think it's this way. I think I've written this backwards. But maybe it's right. Since p must be a constant, but also integrate over 1. I was getting a bit tired at this point. Over the whole domain of AB. Let me just check this with the actual book. So this was in Monte Carlo Basics. And this was... Oh, no, it is. Okay, that was right. So 1 over AB. Yeah, I was just making sure that that's right. I think I should also, for my own sanity, kind of do the same here. Just kind of add it in. Okay. We are asking here that the expected value of the returned of the result of the integral Okay, so this is us evaluating. This is us, well, seeing what the value is. Okay, so here we are taking the expected value and replacing it with, so this is all still probability, by the way, because Monte Carlo's like randomness means that we're trying to predict the probability that it's getting to the right value. This is the whole, this is us trying to use that for the integral, and then we're just kind of work backwards from that using the expected value to get out the integral, which is what, you know, a one-dimensional integral looks like by that. Okay, so here we are taking the expected value and replacing it with what it would be if we just integrated over the range instead. So yes, we're not doing that, we're just integrating over the whole range. Here we are using the probability density function, you know, we talked about before, to simplify the integral to, this integrates to 1. Remember that the whole domain is 1 over n. I've uploaded the code and some context, so you can see the code generates features. You can check out the meta info. Thank you. I appreciate that, dude. Honestly, yeah, it's always good to like learn these things. Yes, and well done for working your way into the server. I know it's sometimes tricky depending on you know, your location. So yeah, I appreciate the effort you put in there. Okay, so this works for any integral for high dimensions. The only difference here is that the b minus a goes over all the range in all the dimensions. So let's play some music, because I think we've ended. What have we got? So if I go to cinema mode, I think it's easier to select the video. Nope. Okay. Let's go with. Yeah, let's do this again. This was a good playlist. A bit of old school RuneScape for the vibes. Okay, so reducing errors in the Monte Carlo estimator. We can remove some of the restrictions we have when we originally defined the Monte Carlo estimator. This is important since choosing the probability density function, we can we were sorry, let me read this again. So choosing the probability density function, I think it's get rid of where the samples are drawn from leads to a key technique for reducing errors in the Monte Carlo. In the random variable xi are drawn. It's not. I said drawn. They're drawn from us. I'm just trying to put my water in a place that doesn't get knocked over. Okie dokie. Drawn from our probability distribution function, then the estimator looks like this. So it's basically the same thing as before, but the domain is over n samples instead of the domain, and the function that we care about, which is what we did here, is now divided by the probability density function as the denominator, and we just make sure we just don't divide by 0, and like we're all good, right? And the probability density function just allows us to accurately pick, find random values that are sampled more accurately. So there's two, yeah, so the only restriction is the probability density function must be not 0 for all values of x, where x, where the absolute value of the function x is greater than 1. This is because this means that you can't have a function, a probability density function over a uniform domain where there's just one value that you can select from. that would mean that we have we would have 0 over some of the values of the uniform when over the domain, right? If is similar, this is similar and not too hard to see the to what we worked out before with our let's take this, which doesn't exist yet, but it will. Yeah. With our okay, this is similar to what we worked out before with our Monte Carlo estimator, not that to see the this is similar to what we looked at, what we worked out before with our Monte Carlo estimator, to see the aspect I was confused and I was like, what is it talking about aspect for? Expected value of this estimator for an integral. Yep, so we take the expected value, we then do what we did earlier. So we turn the... So we're skipping a step here, we're kind of doing this. We go from that expected value to this, and then we just integrate over whatever the expected value was supposed to be. Which changes our probability density function to our commutative probability function, which if you remember, when you integrate the probability density function, you get the probability commutative function. So this is what the small p is. So I should actually write that down, because that's actually something I might forget in the future. Here, remember when we integrate over this thing, we get the commutative distribution function, as far as I can tell. This fella, because that's the derivative. We get the probability, and the derivative is the integral, just backwards, right? So there we go. Then we can just simplify everything down, and then we do 1 over n samples over n. We can just get rid of that, and we get back to our integral. So that means that we are estimating over the correct integral. We can now understand why, when we were breaking down the light transport equation, we used an expected value of 1 over 4 pi. We were sampling over a uniformly over a unit sphere, which has the area of 4 pi. Since the probability density function is normalized over the sampling domain, it must have a constant value of 1 over pi. I hope you see the connection between the Monte Carlo estimator and the broken down light transport equation. Yeah, so I had to put that in there because I didn't want to have to like rewrite the light transport equation. Whoops. Stuff. We can't use something like deterministic quadrature technique, whatever, because this increases exponentially in the dimensions of n samples. Dimensions with n samples. We use a as we, unlike with Monte Carlo. I'll just simplify that down. I kind of sad that we missed that. Okay, so errors in Monte Carlo estimators. So we're almost done, and then we can actually start to study. But this is good because I'm missing a bunch of. Yeah, I thought it was difficult there, but in fact, in rows, I got you. Sorry, there, Dimitri, got you. Yeah. Okay, so errors, this is the last bit before we can finish our book. Errors in the Monte Carlo estimators. Just because the Monte Carlo converges at the right answer isn't enough. We need to know how fast it finds the answer. The concept of variance is used to figure out how far the estimated diverges from the expected value. So I don't think I'll need to correct anything anyway. If we have a Monte Carlo estimator f, the variance can be of the expected value can be written like this. So you gotta remember f is the Monte Carlo estimator and e is the expected value, which is just working out the difference between the two, which is just here to show that. If you work out all the squares, then this below is here just to show, okay, using the derivative properties for the expected values in the background probability review, we can change the equation into something like this. If the estimator is a sum of independent variables, like Monte Carlo Fn, this all works out to be the variance of the sum of the independent random variables variance, which is really nice. Because that means we can just say, okay, what are the variance of the random variables? All right, that is also the random variable. That is also the convergence of our Monte Carlo. Okay, so the variance decreases linearly with the number of samples because we are summing them. The high variance power, the higher the variance power is, the lower the convergence. So a variance number that's a square, the convergence is O of 1 over root n, where n is the number of samples. We can see this if we watch a Monte Carlo estimator send out samples for each pixel. It rapidly improves the quality of the image at first, but the samples increase. As the samples increase, this rapidly decreases, meaning that the errors get harder to remove the fewer they are. As we can see, we increase. In this graph, we increase. As we increase, in the x-axis, which would be the number of samples, we are converging, correcting mistakes, but at a increasingly slower rate. So I think I got to this. Comparing estimators. The linear decrease in variance with the increasing number of samples makes it easy to compare estimators. How do we compare estimators then? Yay, we did revision. Woohoo! Now we can start this at... Alright, here. So this is the last part that we didn't finish yesterday. No. Where is the... What am I interested in here? Errors in multicolor estimators. We did that. Oh, okay, here. We're actually very close to the bottom. So I hope to get through this today. This part. And then the rest is like a bit more graphics related rather than just pure maths. Because I'm not a mathematician, and this has been a bit of a struggle. I expected this to take a couple of hours, like nearly 2 hours to review, because I need to do revision when I've studied this much. But I'm just going to head to the loo real quick. I hope everyone is enjoying the stream so far. Thank you for anyone who has turned up and is enjoying it. Feel free to ask questions, by the way, about things that I'm doing. I can always demonstrate things. Right, yeah, so I'll be right back. Yes, I'll leave the music on there. And also pause this, because we are not doing anything anymore. Okay, cool. Let's bring this up. Alright, see you in a sec. Hello, made it back. Hope you're all good. So yeah, now we're going to break into actively studying new stuff that I don't know, which won't be as fast. So, because I don't know how to do any of this yet, like how to estimate, compare estimators for our Monte Carlo madness. Okay, so linear. So I'm reading from here. This, if you're interested in this book, I'll post this in the chat actually. So where I'm getting all my notes from and where I'm studying, I'll throw this in here. This is the book that I'm reading from. If you want to check it out, I think I shared this yesterday, but just to it's a physically based rendering book. It's pretty intense, but it's mostly focused on how to do physically based rendering with ray tracers. That's why we're doing Monte Carlo, right? But yeah, it's pretty maths heavy. Let's to put it lightly. But it's really good. It's really good. Anyway, the linear decrease in variance with increasing numbers of samples makes it easy to compare different Monte Carlo estimators. Consider two estimators where the second one has half the variance of the first, making half the variance of the first, but takes 3 times as long to compute an estimate. So it has less variance. Interesting. In this case, the first is preferable. So the second one has half the variance as the first, but The first takes 3 times as long to compute an estimated value. Really? That's okay. Let's see that again. Consider 2 estimators where 2 has the... So where the second has half the variance of the first. So the second has half the variance, but takes 3 times as long to compute. Excuse me. So the second has half the variance, but it takes 3 times as long. Which of the 2 is better? In that case, the first is preferable, because it just takes less time. It could take 3 times as many samples in this time consumed by the second. In which case it would be 3x variance reduction. I see. Okay, so it's about speed, because we can do more estimators. We can do more samples. Well, consider this example where we have a estimator. We have 2 estimators. Oops, that's not how you spell it. Estimators. Right, I'm going to kind of list these out so it's easier to read. This estimator has half the variance but say A, B, however, let's say A and B. The A estimator has half the variance of B. But B is 3 times faster than A, which B itchy nose is preferred over A, because we can 3x the number of samples, which would reduce the variance over by 3x, beating A. Okay, so this concept can be encapsulated by the efficiency of F, which is defined by 1 over VT, 1 over VF TF, where VF is the variance and TF is the running time to compute the variable. To work out the efficiency, we use this equation. Okay, back to LaTeX. Everyone's favorite programming language. So that I need to look up the Greek letters in LaTeX. Greek letters in LaTeX. Yeah, I just need to see a list of them, thank you. So epsilon, that is epsilon. Okay, so epsilon. Yeah, I don't know the Greek symbols off the top of my head. Shocking, I know. Terrible. We can use this efficiency. We can work out the efficiency using this equation for a estimator. F n. Let's just say F. Okay, so epsilon F equals, so frac 1 v, so the variance of the function divided by time. I'm gonna grab these guys, so I can just copy and paste this into a LaTeX. Where, oops, where is the variance and is the time to compute. Not all estimators of an integral have expected values that are equal to the value of the integral. Okay. Such estimators are said to be biased, where the difference. Okay. Some. Okay, so this might be a new thing. A new note. Biased. Oops, biased. Estimator. Estimators. Okay, so not all estimators of an integral have the same expected value of the integral. These are considered bias the estimators. Where the difference is worked out by a simple subtraction. Okay, so beta is equal to E, expected value of F, minus int, nope, don't need to do anything, F x dx. Alright, cool. Bias estimators may still be desirable if they are able to get close to the correct value more quickly than unbiased estimators. Carlos and Whitlock in 1986 gave the following example. Okay, so it may be better to use an estimator that's biased if it can get close to the not color, close to the expected value much faster than a non-biased estimator. Okay. So Collis and Witt gave an example. Consider the problem of computing an estimator of the mean value of a uniform distribution. Consider the problem of computing an estimator of the mean value of a uniform distribution of random value x over p. V, I don't know what that tilde means, but p over the interval from 0 to 1. One estimator could use, one could use this, or you could use the bias estimator. So just return the max value divided by 2. The first estimator is unbiased, but has the variance of minus 1 O of n to the power of 1, so square root. No, whatever, negative 1 power. The second estimator expected value is okay. So it is biased, although the variance is -2, which is much better. This estimator has the useful property that its error goes to 0 in the limit as the number of samples goes to infinity. Such estimators are consistent. Most of the Monte Carlo estimators used in PBRT are unbiased, with a notable exception of the... Okay, so the stochastic photonic progressive... what is it called? I keep forgetting what this is called. Yeah, no, I don't think it's negative variance. That's the variance, like how it not negative variance. That'd be how fast it converges, I think, based on the variance. But let me look up this quickly just to remind myself. Graphics theory, stochastic progressive photonic mapping. I keep forgetting what that's called. So, with the exception of this stochastic photonic progression mapping, which implements a photonic mapping algorithm. Okay, so this would be really clear to a mathematician, but this is a bit lost on me, to be honest. Because as far as I can tell, this is a function that returns the max value, right? So that'll just be half of the max value for the number of samples. Okay, so what are we trying to work out here? Okay, so consider the problem of computing an estimator of the mean... Computing an estimator of the mean value of... give the Following example, consider the problem of computing an estimator of the mean. Oh, the mean value. Right. Okay, so it's trying to work out the mean value of a uniform distribution. Okay. Right. Yeah. Okay. Right. I didn't quite understand what we were trying to figure out. Okay. I was like, what? Okay. So consider working out the mean value of a uniform distribution over the interval of 0 to 1 over 0 to 1 with random sampling of x underscore I. So yeah, the variance would should be greater than or equal to 0, but its expected value of a square. Right, I'll dig into that in a minute. Let's, because I'm quite a little. I've got to go a little slower than I think you could probably. There are two estimators. In this example, sorry, you could use two. You could use two estimators. One bias and one not biased. Ugh. I just saw my mustache. There we go. Okay. Okay. So. Okay. So we have a frac 1/n, which would be the samples. Slash sum. Oops. Press the wrong key. Now is equal to 1. That's where we start. And we get to n samples. This is like the standard way of working out the mean, which you would do in high school. Or you could use the bias one. Estimator. Okay, so frac 1, 2. I assume back max is a thing. Yep. So x1 comma dot n 2. The first estimator is unbiased, but it has a variance with the order of. So that's how it vary. I wonder if I could graph that maybe. Yeah, let's see. let's see if I can graph that, because that would be nicer to just refer to. Desmos. Desmos. That's not how you spell it. I know it is. So y is equal to x to the power of -1. And then what is 2? So I assume that we converge. Yeah, we're converging way faster as the number of samples increase. So the variance in the variance is just so different. Okay, so I'll grab that in a second. The non-biased one variance with an order of n to the power of -1, and one over x2 tends to 0 way faster. Yeah, which is that's what I did, right? You've written the same thing. Yeah. So that's just to help me visualize it. Yeah. You just did the conversion of 1 over instead of negative. Yes, thank you for that clarification. Oops, that has not. I think I need to do this maybe. Yeah. Okay. And the bias one. The second estimator is expected value is okay. 0.5 and then frac you, man. N plus 1 is the rate not equal something? EQ? Yes! Okay. I didn't want to have to look that up because that would just take time. Okay. But has a variance of O and that's much better, as you can see in this graph. The red is the first variance, first estimator meters variance, and the blue is the second estimator's variance. Hey bro, hey dude, what are you doing? So I'm working, I'll just type this out and I will get to that question shortly, but yeah, thanks for joining us. So I'm just going to copy and paste a image to explain the difference between two things, and then I'll explain what I'm doing, which thank you for asking, by the way. It's nice to get nice questions like that, because it makes me there you go. So oops, nope, this, paste. I'll just rename this converging variants. So, yes, we are studying right now. Anyway, I'm live streaming studying lighting. I am making this game, and I want to accurately display. The graph is scaring me. Yeah, I want to display light more accurately than I currently am. If I turn off all the debug geometry in this space game, this duck will soon be a spaceship, right? You can see that everything's really dark, and there's a couple of issues that I have with my asteroids. They light up weird depending on the direction. So I just don't know lighting theory very well. I've gotten better over the past couple of days. So we are trying to get it so that we can have nice effects when we actually light up the scene. And we can, do stuff, and it'll be like accurately. We can accurately simulate the sun, physically based the sun, through like a cloud or something like that. So it'll look really cool in space as we fly around and do stuff. So, unfortunately, thank you guys for the compliments. Unfortunately, that requires a lot of study. With things, we will be working on. The game engine, making it better later on. But for now, we're just doing a bit of maths. Gross, right? To be able to learn how to do lighting better. Yes, because things look too dark, especially when you go in this direction. And you just about see an asteroid pop up, you might crash into it, and stuff happens, which we don't want. So, just keep the duck unlit, and ships alone anyway. Yeah, I feel like what I'm going to do is I'm going to sneak a duck into the game. So for the people who've been watching, for the for who've been joining in the live streams and followed the videos and stuff, you'll get like an Easter egg that you'll be able to find, and yeah, I'll see if you can find it. So yeah, the duck will not go away. It'll always be there. It just might be harder to find. Yes, so that's what we're doing. And yes, this book is physically based rendering. The book, it is pretty dense with its information, and we're getting close to the end of this page, which I'm thankful of, because it's it's basically just maths. So yeah, that's what we're up to. And yes, it is all in C++. And Vulkan is used for the renderer. So yeah, I'm trying to match my C++ skills with my graphics skills right now. So this is what we're doing. So yeah, let's keep on. Yeah, thanks for the compliments, guys. And that was so beautiful. Appreciate that. It hopefully will be more beautiful as time goes on, assuming that I keep on with this book. It's one of these things where you've got to study hard for it to make any. Currently, I haven't been able to map its concepts onto my code yet, but that is just going to take more effort. So yeah, let's get on. Oh yes, can I ask another question? How can I get started with game dev? I know basics of C++. Okay, so there's two paths that you can take with game development, and the one more traveled and the one that most people recommend is using a game engine. Now, this is a newer, more beginner-friendly and general path. You can take. Let's pause this for a moment. And it depends on your goals, right? If you want to take this path. This path is for the people who are more design orientated. They have a game idea that they want to share with the world, and they don't really want to spend forever coding, right? Maybe you want to combine some cool ideas, throw some things together, and like put it out there, right? If that's you, you're probably going to benefit from with C++. Maybe picking a game engine that supports C++ as its scripting language, so you can do, this and that. The path that is less traveled and it's harder, but has in my opinion greater rewards for following it, is making your own game engine. And this requires a lot more technical ability, and it takes a lot longer. So this is for the people who, for what I would say for the most part, love doing programming for the sake of programming. So, but you may have an idea in your head that you want to express in a game, but you're going to have to, if you take the I'm going to make my own game engine path, you're going to have to spend, like, doing stuff like this, for example, like I'm reading a book. I would rather just get the lighting nice, but I have to read this to understand it. So what I would say is, it depends on your goal, right? Yeah, so Godot supports C++ as far as I know. So you want to make your own game engine, yeah. So if you want to make your own game engine, I would say what you need to focus on is making sure that you know more than the basics of C++. And just, I made a runner game in Pygame, and that's it. Oh yeah, so you've got some experience, which is nice. So make sure, in my opinion, that you have a good foundation of breadth when it comes to C++, if you're going to use C++ as your game development language. So that should be, I should be able to quiz you on things like what's the difference between a reference and a pointer? What's a function member versus a free floating function? What's static mean? If I want to make a singleton, how would I do that? These are the things that you should kind of know before diving into making a game engine. That's what I would recommend, just so you have a nice foundation to launch into rendering and all that kind of stuff. Because if you go straight into that, which you can, which is fine. I'm not saying you can't do that. C++ might just get in the way, and you don't really want to have that friction there when you're like learning something more advanced. So make sure that you've got a nice foundation of C++ there, to make sure that you get further along, that you can get further along with your. But yeah, that is also, it's like, what should you do? In my opinion, I would go to learncpp.com just to give you the full course. If I was to teach you, I would take you to LearnCPP, which is often updated every now and again. So go to LearnCPP, right? And also pair that with One Lone Coder's early videos, right? So that should be your studying in C++. So, like uninitialized variables, read this, right? And then I would go to YouTube personally. If you're making your own game engine and this is what you want to do, I would go to One Lone Coder and pick one of his early projects. So One Lone Coder. And here he is, this guy. I don't know. Well, he was once called One Lone Coder. I don't know how to say this. So yeah, pick one of his early. Go to oldest and pick something like the Tetris video, this FPS ASCII thing. Learning how to make Tetris. There's the Tetris one. If you're interested in, pick a project that makes sense for you. If you have Learn CPP and this together, you'll be building skills. And I've actually told someone to do this. And if I just bring up their project, this is what they were able to achieve in their C++, right? They made the Tetris clone, they put everything in main, but it's really well written. This is a really well written console application for a game, and this will help you kind of understand like how games work. This is like what you should be aiming for, making sure like it's only 266 lines, and I think it's very achievable if you pair these two together. So this is what I would. This is the path I would take you down if you were interested in making your own game engine, and then you can see if it's actually interesting, right? You may not like it. Maybe then you can like, okay, I've learned some skills, and you can transfer that over to another game engine, right? So that's what I would do, right? So yeah, that's hopefully that was helpful. Hello, brother. You seem to love studying. How much time do you dedicate to your studies? I want to study like you, but I lose motivation every time. I am very motivated right now to make things work because I don't have all the time in the world, so I'm under a lot of pressure, and that pressure is making me work harder. Streaming also is helping a lot. I don't know if this is a solution for everyone, but if I'm, for example, goofing off watching videos, the stream's going to get really boring and people are going to be like, what are you doing? This is not what we signed up for to watch. So yeah, there's a lot of small things. I really want to make a game that you guys want to play, so I have a lot of player expectations on me. So there's a lot of like small, a lot of small. Should just have this open. I mean, I've got Discord. It's fine opening up Discord. So yeah. There's it's a tricky one. We can talk about motivation maybe. But how would I get more motivated if I wasn't motivated? I would say pick things that make sense for you to study, that are easy if you're starting out. For me, it's like what I want to be able to do is if I go to my notes real quick, just this is like a motivation of mine, right? I want to be able to pull off these type of lighting techniques. It's quite small, these images, but these look, in my opinion, absolutely incredible. And they are physically based, which means, oh, there's the abstract. Physically based, but to understand this paper and implement it properly in a raster-based engine, like, I need to get better. So I have this drive in me to get better. So there's things like that can help. That's very specific to me, though. So I just find if you're starting out, especially, just find something that's small and try and enjoy the process of learning. Thank you, by the way, Heisenberg, for the nice compliments there. How do you gain advantage in knowledge in these things, like tutorials? Yes, you need a breadth of knowledge, not just the depth of knowledge, right? So a tutorial will take you down a path, like it'll give you some deep knowledge, but you need to make sure you've got a good foundation overall, which would be the idea of studying, what is it called? Learn CPP, for example. That will give you the breadth of knowledge that you need to lay a foundation of work, which would help you with getting out of tutorial hell, for example, that people have. Yes, making tutorials, making a project will learn you. That's why I recommend like pairing learning stuff with TT's 100% right here. I would also, yes, make sure you are studying taking a project that's one, manageable, and two, actually interesting for you personally. And you'll kind of learn. I'm 32, so yes, I've graduated university. So yeah, some may call me Unk, some may call me Young, depending on your age. But yeah. Anyway, let's get back into this, right? I would like to get to the end of this page before lunchtime, which is kind of soon. We don't have much left, so I think I can probably I'm gonna say hopefully what I said was useful for people. I know it's tough out there when you're learning things on the internet when everyone's telling you to do this and that. And I should quick mention before I start rereading this. Don't get AI to write your code for you. This is a trap. Your projects will be easier to write, especially if you're a beginner, and the end product will be better, but your skills will degrade if you do that. And if you care about making something by yourself with a game engine, your skills need to be good. So avoid that trap, especially early on. But anyway, so no problem. I'm glad I could help you guys. Young, yeah, I'm young. I'll be back with my game one day. Yes, please. If any of you make a game, I would love to play it. Honestly, seriously, it's just a quick thing. In my community, I keep saying this, I would love everyone in my community who's interested in doing the same thing I am to be more successful than I am, while I'm also trying my hardest. So if you guys can be more successful than me, that would be, a dream come true. So, I wish you all the best in what you're doing. Anyway, so which includes new people and old people who've been around for a while. Keep on keeping on. Anyway, so some estimators have nice properties. Have nice properties. Where as the samples. Whoops. That's not what I wanted to press. Yeah, hard to do too, guys. N goes to infinity. The errors found in the bias go to 0. This is what we call a consistent estimator. An example of one is the biased estimator in this note. Cool. Okay, so let's keep reading. So I'm not that concerned about. Okay, so there's the progressive photonic. Again, I've forgotten what it is. Stochastic progressive photonic mapper estimator. I'm just kind of so I don't need to take notes on this specifically, but if I will do ray tracing for that stochastic progressive photonic blah blah mapping, there we go, then it'll be good to know that we need a biased Monte Carlo estimator. Anyway, so closely related to the variance is the mean square error, which is defined as the expectation of the squared difference of an estimator. Okay, so closely related to the variance is the mean. Okay, so this is different. I can split this up again. The mean squared error for estimators. Okay. Okay, so closely related to the variance is mean squared estimator, which is defined as the expectation of the difference of the squared difference of the estimator and the true value. Okay, so remember that an estimator is trying to work out the value of an integral. Okay. The mean squared error MSE, right, is defined as the expectation of the squared difference of an estimator and the true value. This seems a bit random, but here we are. Okay, so why do we need this? I'm sure we'll find out. What keys? Oh, keyboards. Do you have, by the way? Is that what you're asking? What keyboards I have? It's pretty disappointing if you want to know. I'm not a big keyboard guy, but here, just in case that was what you're asking, I'll just say it's a one I just pulled off Amazon. I don't really like mechanical keyboards, never have. So my my keyboard is like the cheapest thing that you can get off Amazon, because I like to be able to smear over the keyboards, if that makes sense. So it's called a Victising keyboard. It's basically, if you bought a Logitech, like a basic Logitech wired keyboard, made in China and all that kind of stuff, you would basically end up with the same thing, right? Like I said, I like to be, I know it seems silly, but I like to be able to easily go, you know, I like to be able to easily do that without the mechanical keys getting in the way. Because I like to, like, you know, where I find that hard to do with like really pressy keyboards. So mine's more like a laptop, almost, not quite, but almost like a laptop keyboard. Oh, hi Rash, Code. A little tip to save you time: if you use Gemini for learning and taking notes, it will save your time. Try just once. That is, yeah. Thanks for the thanks for the tip. For me, I would prefer the information to filter through my own brain so I can explain it to myself clearly. That's why I'm taking longer with this. It's a long-term strategy to have higher retention. I never ever want to read this book ever again. That's the goal. That's why I'm going slower than people typically would. Just one with low activation weight. Yeah, pretty much. I just like low activation weight. I guess I could get a mechanical keyboard with low activation weight, but the ones I've tried, I got like super clunky high activation weight. It is possible to work out the variance on MSE of some simple estimators in closed form, but for most of the ones we're interested in rendering, it is not possible yet. It is still useful to be able to quantify these values. For this purpose, the sample variance can be computed using a set of independent random variables. Oh my goodness, we do random variables for working out this as well. The equation 2.8 points at the equation 2.8 points at one way to compute the sample variance for a set of n random variables. Okay, if the sample mean is computed as the average of x 1 over thingy, then the sample variance is okay. Yeah, it's pretty much, it's all been about, yeah, it always has been. Alright, so always has been random variables all the way down. Okay, so you really can't work out the variance or MSE, mean squared error. Just make that bold. Mean squared error. With rendering equation Is it estimators we're doing? Yeah, yeah, must be estimators. So, to work out both, you need to sample some random variables xi. Okay. So what's this equation 2,8? I don't remember it. Please don't. Oh, okay. So 2,8. Oh, it's this. Okay, so using the equation, I'm just going to type this out because it's just going to be easier for me in the future to read this. B F equals, oops, it's not that, it's one of the easy ones to type out. So E F minus E two. Okay. Is the way you calculate. Sorry, I'm just going to try to get through this before I read chat again. Calculate, just so I don't forget things. Variance. To compute this with random samples. Using the set of independent variables, the equation, one way to compute the sample variance for a set of random variables n over x. Okay, so we have two things we're working out here. We just take a set of independent random variables xi. Okay. Where do we put them? That's the question. In the... So that's the accumulate... There's no function here. For the purpose of sample variance can be computed using a set of independent random variables. The equation 2,8 is one way of computing the sample variance for a set of some random numbers. So a set of n, which will be the samples of, if this, okay. Where do we put the random variables though in this equation? Do we put them in F? And then, but yet it is still useful to be able to quantify these results. For this purpose, the sample variance can be computed using a set of independent variables xi. Yeah, the random equation once again. Yeah, isn't the point of taking notes that you have to work out the material? And yes, pretty much. That's what I'm doing. Okay, so the independent random variables. so are we at the bottom basically? Yep. Sample variance can be computed using a set of independent variables. The equation, which I wrote down, at points at one way to compute the sample variance for a set of n samples, a set of n random variables xi. Okay, so we and sample over the equation. Oh, I understand now. I think above where f takes in the samples. All right, so as far as I can tell, because f is a estimator, we literally just throw in the values into the estimator and just run the variance equation on top of that. So yeah, that would make sense that you can't figure out the variance. Yeah, you can't figure out the variance because analytically, I guess. Analytically. Right. Okay, my brain is not wanting to. My brain is not helping me retain his words. That's just nonsense gibberish, that one. Okay, let me look up analytically. Yeah. Okay. So there we go. There's F's and T's and X's and W's in there. So let's actually use the right word. Because that would require us to analytically solve the integral the estimator is estimating to know its variance from the value, from the actual value. Yeah, okay, so that makes sense. It's really hard for me to understand documents unless it's technical or mathematical. Oh, okay. I end up just stop writing notes manually. I think I understand well enough from. Oh, especially if they're technical, mathematical. Any tips for understanding these guys? Well, this is where probably we would deviate on our approaches. I personally want to know this well enough that I could be quizzed on it and take an exam on it and be able to then, you know, answer the questions correctly. So I effectively explain this to myself. Like literally, I wrote extra stuff here, right? You can't figure out the variance of analytically because it would require us to analytically solve the integral the estimator is estimating to know its variance from the actual value. Now, what I'm saying here is like, this is not in the document at all. It just assumes that you know this. That's what it's kind of assuming in these couple of lines. So you've got to figure out when you're not understanding something like I literally just did then. What piece of information are you missing? And that was the piece of information I was missing. Because it was going very quickly over what we needed to solve. So it's about, when it comes to mathematical stuff, finding that foundational piece of information that you need. For example, let's just say that you're trying to teach someone who's very young how multiplication works, but they've never come into the concept of addition. Now you can tell, you can say like, well, if you take 2 times 2, that's the same as 2 add 2, and if 2 times 3 is 2 add 2 add 2. You can say that until you're blue in the face, but if they don't understand what it means to add numbers together, then that doesn't make any sense to them at all. So sometimes that, even, you could say what I'm struggling with is dead easy. I don't know what level of rigor that you're familiar with, but I'm still trying to do that. I'm trying to find that point, that gap in my knowledge for understanding stuff. And it's possible an AI would do that, but that's the reason I don't use an AI, because I want to be able to read these notes in the future and have it explained back to me like when it was fresh to me. So I shouldn't ever need this level of support to understand this concept again. But just in case I completely forget everything, then I can reread this and have this all explained to me based on the foundation of knowledge I don't have, right? So that's what I would do. I would make sure that you're burrowing out that piece of knowledge that you don't understand and then explain it to yourself so your future self can thank you when you look at your own notes. And that's why I don't use AI, because AI is going to do that process for me. And that friction of finding that piece of information is the learning. That's how you learn. It's not acquiring the information. It's the friction of overcoming the challenge of not understanding something. But, everyone has their own approach. I'm not going to say mine is the correct be all and end all, but, yeah, that's what I would do personally. Hopefully that's a little bit helpful. Maybe you can take something away from that. Maybe not. I hope it was useful. But anyway, let's get back into this. If the sample mean is computed as the average of this, so that's the average, then the sample variance can be worked out like this. Okay, so because of the sample, remember. So if the sample mean, sample mean is computed as the average, which would be how do I write that in LaTeX? Let's try x I can just use another letter, like ABG or something. Yeah, I'm just gonna do that. That's just gonna be easier. Which is just the average of all the numbers. So this is the average. If we take the average of the random samples with this thing, dash n, then we have a sum x underscore I, then the sample so sample variance is what? So I'm gonna go frac 1 n minus 1, so that's the samples, slash sum okay, so underscore n, I equals 1, that's where we start. This is how many we loop over when we're adding things together. For those who are wondering, the sigma notation, or the sum notation, is just a for loop. Starting from I equals 1, ending at ending at n. So, if you're wondering what that means, it's literally just a for loop if you're familiar with programming. That hopefully should make things a bit clearer. You actually learn from reading / being told stuff. Learning only happens once you compare it from your previous knowledge and just your mental model, pretty much. Do you think in the belief in God / religion is useful? I'm going to pass on that question. That's not really the stream for it. But yeah, you do you with your thoughts and religion and stuff. The division by n minus 1 rather than n is the Basel's correction and ensures that the sample variance is unbiased. Is an unbiased estimator of the variance. Yeah, mathematicians. Yeah, 100%. That's funny. Okay, so the division by n minus 1 rather than n is the... I love this song, it's my favourite. One of my favourites in RuneScape. If you can hear it. I hope it's not too loud or too quiet, but it's like turbo nostalgia for me, this one. Variance is unbiased. Estimate of the variance. Nice. Right, I believe you on that one. I won't need to look that up. Okay, so the sample variance is itself an estimate of the variance. Yeah. So, oh my goodness, that also has variance. Okay. Consider. So we have an estimator. Okay, so we have the rendering equation, and then we have an estimator that estimates the rendering equation. And then we have a variance to see how far that's off that rendering equation. And then we have a variance. And then we have a variance for that variance to figure out how far the variance is off. Okay. Variance is all the way down, I guess. You slide the sample variance is an estimate on the actual variance. So it's sometimes useful to figure out the variance of the sample variance. Very good. That was so close though. Consider an example: a random variable that has a value of 1 99.9% of the time, and a value of 1 million 0.01% of the time. If you took 10 random samples of it that all had the value of 1, the sample variance would suggest that the random variable had a zero variance, even though its variance is actually much higher. Variance is a real value, not a random variable though, so it can't have any variance. yes, so we have sample variance though, which is like because we can't work out the actual variance of our estimators, we have to basically sample into the estimator to work out the variance based on this equation. So that means we need to work out the variance of that sample variance that we sample with random numbers. So that's why we're doing this, which is kind of nuts that we're in this situation. Yeah, no, exactly. Exactly. Consider we have a random variable that has a value of 1, 99, should do this in thingy maybe, 99%, 99.9%, oh, is that not going to work? Escape that, of the time, and 1 million, let's just write this out. Zero, oops, what do I do? 0.01 \% of the time. If we took 10 random samples, it would all have the, it's extremely likely that it would tell us that we have 0 variance on our sample variance. Which is wrong. Okay, so if we accurately estimate the integral f can be computed, for example, using a large number of samples, then the mean square error can be estimated by this. The image tool utility program that is provided in the PBRT distribution can compute an image's mean square error with the respect to a reference image via its diff tool. Okay, so that's just telling me what it's used for, but if an accurate estimate of the integral f tilde is what is it, estimate value, can be computed, for example using a large load of samples, then the mean square error can be estimated by, okay, so if we can work out if we can estimate, accurately maybe, estimate the integral, let's write this down, I guess, def, how do I write this? It's not equals. LaTeX. We're almost there, guys. I'm so excited. Estimate equals, I don't know what it's, nope. Just go to here. Hopefully this has a big list. So equals approx. Yes, I remember now. Oops. Whoa. Okay. Thank you, internet, for sending me all that junk. Okay. Cool. Let's go back to this. Okay, so int f x dx. Oops, not c. Sample using loads of samples. We can compute the mean square error, the MSE, like this. Sorry, we can not compute, but we can estimate. Fantastic. Okay, so just this, and I think we're pretty much done for this page, which is fantastic because this has taken 2 days. Well, a day and a half. And now I can go eat afterwards because I think I understand this as far as I can tell. So for the mean square error for an an estimator is equal to its frac. Oh, 1n. So then sum underscore we started I equals 1. Oh, we go to n. Oops, needs to make that at the top. And we go f random samples over, so that's the random variable, and okay, so minus the I need to make this a new symbol. Is there a way to put a symbol on top of you like this? No. Let's just check. What did that do? Okay, nothing. So if I go underscore then this, maybe that works? No. Let's just make a new letter, I guess. Yes, I guess. It's kind of lame, but at least it translates to here, est. It's kind of a variable instead of a mass. People will hate me for doing that. So the image tool, so you can use this to diff images. From a reference image to see how accurate you are. Fantastic. Okay, so what I really need to do next is split up all this into. So how I do this is I have a source note, just for people who are wondering, and I split these up into little bits because I'll never. Well, the idea is that if I just want to read this, for example, you know, how to estimate like the mean square error for estimated. So I think this is actually better if I say working out variance and the mean square mean maybe MSE for estimators, right? Yeah, so I split these off into like subheadings so I can then make notes on them and then I can come back. I can circle back to all this instead of having to read the whole thing. I can, yeah. So what I'm going to do next is split up all this into little notes and kind of connect everything together in here, which is going to take a minute, but it's definitely worth doing because it's easier to review in the future. And I don't want to have to like curse at my old self because I made everything into a massive long essay every single time. I want to review one concept. So yeah, so what's the next thing? Okay, so it's just more maths. But we have a use of the what is it? The probability density function when it comes to our estimator. What else do we have? We have what does it say? Multiple importance sampling. So this is actually how we do the sampling. Oh, look at that! A bit of code. Ooh, we're getting back to computers as we go. So it looks like we're going to have another section of maths to plow through. But like I said today, we're going to be doing a bit of coding outside of just studying today. Yeah, so I'm kind of curious, like how much maths do we have to go through? So we have, I'm just going to keep this. So we've done this one. Then there's that one, which is what's next. Then this, which is, looks like statistics maybe? Okay, so it's getting more code heavy. Sure. And so okay, so it looks like this is less dense. Looks like it's about transforms. I don't really know though. Previous. I assume this is how to improve the sampling method, and this is, oops, this, and this is about improving efficiency of our estimator per sample. So this is actually pretty big, but I think once we've gone through this one, the rest will get easier. So yeah, I'm gonna go to some of my lunch, and I'm gonna probably put on a video on maybe a Monte Carlo just to give me like a good refresh on what we've done. Unless someone has a, so let's find a video before we can watch. I will go and push to talk because so Monty, this is just for lunchtime. Explained maybe. I'll just type Monte Carlo, see what comes up. So yeah, we could do that. That's a good one. Because the idea of learning all this is to do physically based rendering. So let's go to Ace Roller, which I am subscribed to, but I think it's gonna be easier to type his name in because he's buried in my subscriptions for some reason. PBR. Yeah, let's go for the yeah, let's I believe this is it. Just make sure it's not anything else. I'm going to start watching just to, I'll turn this up as well once we,
Disney movies are filled with tons of
yeah, so it's going to if it's talking about lighting and how that's going to be done, it's going to be this. We won't watch all of it. I'll just watch, typically it takes me about 15 minutes as I've learned through live streaming to eat my food. So this, we'll probably watch like half of this and maybe half of this next stream. Sound good? I will be right back though. I will thank you for that suggestion, TT, because it is something I probably do need to watch if I'm going further and further into the rabbit hole of physically accurate lighting. So I'm just gonna grab my food. Don't push to talk. I'll make this bigger so you can see it. Yeah, I hope everyone's enjoyed the stream so far. I've had fun. It's been really fun learning this stuff, and it's nice to have learned all the stuff that I did yesterday, and then like be able to continue with that without much struggle, which was nice. Okay, so I'll be right back, guys. See you in a minute. I'll leave the music on for you all. Hello, just setting right back up. Just getting everything. Oops. Let's not knock over everything. It's pretty tricky to get into my super scuff setup. I've got to stand on an office chair. So you probably hear me. Okay. So, Ace Rolla video. So yeah, I've got my food. My Greek yogurt's gone a bit weird, but I don't know why it's done that. So yeah, so your ears don't get you know, you don't hear me chewing and clanging of cutlery and stuff. I will be on push to talk, but let's get the audio. Oops, that's not what I want to do. I just want to pause that. So I'm just gonna increase the audio to roughly 70 ish. So yeah, feel free to comment if this is too loud or too quiet when we hear this video. So yeah, I will bring up Ace Roller. We'll say we're studying because this is relevant. And I'll turn this up a little bit. Yeah, let me know if this is too loud, too quiet. We can always fix the audio. Again, push to talk, so alright. Let's go.
Hello everyone! Disney movies are filled with tons of distinctly different surfaces, from sparkly snow, to skin, to linen. All these materials behave differently enough that you'd think each one is programmed individually. But actually, everything in the scene uses the exact same mathematical model, enabling artists to model as many materials as they want, with just one very powerful tool. The math that drives Disney's shading model is the same math that drives every modern shading model. From ultra-photorealistic graphics to Disney's and DreamWorks' stylized graphics, this is what connects it all behind the scenes. It starts at the beginning with the god of graphics, our guiding star, the one that points the way. The rendering equation. While it might look complicated, by the end of this video, you'll understand how games with ultra-realistic graphics like God of War are only a few lever pulls away from looking like Wreck-It Ralph. Most people are never taught or come to conceptualize what math actually is. Math is not real. It is essentially a cartoon of reality. By taking measurements and making personal observations of real-world phenomena, we do our best to construct mathematical models that closely match the behavior that was measured or observed. With a proper model, we can use it as a replacement for reality to predict future outcomes, or in the case of computer graphics, visualize the results, or make intentional adjustments to the model to stylize and create a new reality. Once you get to any problems of substance though, you begin to understand just just how diverse, unpredictable, and chaotic the real world is, and math switches gears from talking in simple absolutes to talking in hypotheticals to obtain good enough approximations. Rather than knowing the solution, we model what a solution should look like, and if a solution exists, it matches what we need, essentially a model for a model. This brings us to this video's problem. Given a point on a surface, how do you determine how much light is going out in a specific direction? This is the fundamental problem of computer graphics, as the resulting light ray from this process becomes the color of a pixel in the final image render, so it's like the most important part. You might be thinking, if the problem can be described in one sentence, it must not be that complicated. But if you take a moment to look around, you can immediately prove yourself wrong. Just looking to the right from my computer, I can already see at least 10 surfaces that all behave in very different ways. Even the plastics are distinct from each other. While we can totally model each surface individually, there's one thing that connects them all: the fact that light goes in and light goes out. So if we want a general model that can do it all, then we need to start at the highest level of abstraction and construct a more sophisticated solution on top of it. This brings us to 1986, when David Immel and James Kajiya introduced a general equation to describe the expected behavior of light surface interactions. Bear with me here, this one is a lot to take in. The amount of outgoing light at a point on a surface is equal to the emitted light plus the reflected light. This is the rendering equation.
Yes. Oh my goodness, if that was summed up earlier. It's taken me such a long time to understand that. Diffuse specular equals outgoing light.
If you think this is too simple, just remember that you're the one that convinced yourself that math has to be complicated. The rendering equation is the holy mother of graphics, and every lighting model across every engine is an attempt to solve it, whether intentional or not. I say attempt because there is no exact solution. Everybody has their own solutions, with their own pros and cons, as well as subtle differences. This is why you can usually tell if a game is made in Unreal, because you're familiar with the Unreal Engine lighting model at this point, whereas a game made in a proprietary engine has its own approach, and thus feels a little bit different enough to be unique. Today, we'll be looking at Disney's solution to the rendering equation, and how they used just one shading model to create every single distinct surface in Wreck-It Ralph and future movies, which is quite the powerful tool. But first, something a little different. This video has been sponsored by Helix. Helix provides premium mattresses.
That's it, the rendering equation. Dun dun dun. Rendering equation. Alright, I'm going to skip this, but support this guy if you like him. If you're going to buy a mattress, get this mattress, I guess. Very cool, right. Blah, 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 blah. Cute cat, though. Alright.
Communicates the fundamental idea. The part we mostly care about is the reflected light portion, because emissive light is usually just an additive constant when we want to model something like a light bulb or anything else that produces light. If we wanted to make that fancier, like have an emitter that is anisotropic or strobes, then we would make modifications to that portion of the equation, but otherwise,
okay.
we can kind of just ignore it, since most surfaces are not emissive anyways. Without emission, the
Hello. Just watching this while I eat my lunch. We're studying the physically based rendering.
The equation reduces to just the outgoing light being equal to the reflected incoming light, and now we have to convert this abstract idea into math that achieves the described behavior because a computer doesn't know what these words mean. Using the least amount of math possible, we define a few variables, such as the position in space, the direction of outgoing.
I'm making a game engine. This is what we're making. Trying to make this better though. Anyway, to avoid chewing on a mic, I will continue to watch this video. Yeah, I hope you're having a good day. Aborted gaming.
Light, which is the direction towards the camera in this context, the direction of incoming light, and the color of that incoming light. Then, to solve the rendering equation, we set the outgoing light equal to the incoming light, and we're all done. To set the scene for our amazing new model, imagine a sphere in a black void with absolutely no light except a single directional light source colored white. Well, that's obviously not right. We are getting what we asked for though. Each point of the sphere is outputting the color of the light source without regard to anything else. If we look at the real world though, we can see that a directly lit sphere looks a bit different. It's brightest where the surface can see the light and slowly gets darker until the surface faces away from the light. Clearly there is a relationship between the direction the surface faces and the amount of light reflected at that point. This means we need a new variable, which is the vector that points orthogonal to the surface, the normal vector. For a flat plane, this vector points directly up. Visualizing the light vector here, if it's directly overhead the normal, then we should expect a full strength reflection, but as the light vector moves away from the normal, below a 90-degree angle, clearly the light should no longer be able to reach that point, and there should be no reflection as the surface itself is blocking the view. Coincidentally, a function exists that takes in an angle and returns 1 when the angle is 0, and returns 0 when the angle is 90 degrees. This function is called cosine. So what we need is the angle between the normal and the light direction, which we call the incident angle, to put into cosine. Thankfully, we can skip that entirely by making use of a linear algebra operation, the dot product. There are two ways to calculate the dot product. The first is by multiplying each component of the vectors and adding them up, or by multiplying the magnitudes of the vectors by the cosine of the angle between them. Since our light and normal vectors are normalized, their magnitudes are equal to 1, and any number multiplied by 1 is the same number, which means the dot product will be equal to just the cosine of the angle. So, if we use this first formula, then through the equivalence of the two definitions, we get what we need. Back to our model, we can write this as either the dot product of the two vectors, or as the cosine of the incident angle. It depends on who's writing the equation. Wikipedia uses the dot product, but Disney uses the cosine, so I'll do that for consistency across resources. The cosine is multiplied with the incoming light color, which attenuates it as the normals of the sphere begin to point away from the light source. But there's one problem. Our lighting is backwards. This is because our incoming light direction is the actual direction of the light, and if we compare the two vectors, we're getting the wrong angle. So in order to simplify, we want our incoming light direction vector to point towards the light source. That way, our dot product trick actually works. If we wanted to model what a white sphere with perfect Lambertian reflectance looks like in a black void with a singular directional light source, we'd be really on the money here. We want a model that can output many kinds of surfaces though, if not every kind of surface. Currently, our model assumes an equal scattering of light in all directions, which we can visualize as a 1. This is obviously quite limiting and fails to accurately portray any surface that is not a perfect light diffuser. As we can see, most surfaces do not scatter light equally in all directions. Shiny surfaces have pinpoint highlights, mirrors do not diffuse any light at all, and some metals even change the color of their highlights. There's such a wide range of complex behaviors here that we have no choice but to once again take an abstract approach and use a placeholder function that describes how much light is reflected at a specific point. This function is known as the bidirectional reflectance distribution function, or BRDF for short, and is the real meat of the rendering equation. We still have some things to add though. For instance, we're only taking into account one light direction, but if we wanted to get the true amount of incoming light at a point, we would need to check every single possible incoming direction in the surrounding hemisphere, which is how we would get global illumination and soft shadows, as observed here, where the light has bounced off the floor and onto the sphere. In math, we model this using an indefinite integral, because there are technically an infinite amount of incoming directions. In real-time rendering though, we're just going to compute one or two light directions, and ignore the integral. Lastly, we bring back our emissive light term from earlier, and we have derived the actual rendering equation written in math terms, not just abstract ideas. This version is a bit outdated though, as it doesn't account for a number of other aspects of light behavior, such as transmission of light observed in translucent surfaces like glass or water, subsurface scattering of light observed in surfaces like jade or foliage, polarization of light, which is hard to explain, phosphorescence, which is when a surface slowly releases light it absorbed earlier, like glow-in-the-dark stars, light interference, which is when the wave of light is interfered with just like other waves can be interfered with, fluorescence, which is like phosphorescence, but the glow ceases immediately after radiation exposure stops, nonlinear light effects such as two-photon absorption. If you want to read about atomic physics, you can go ahead and do that on your own time. Lastly, the Doppler effect also applies to light, but only when objects are traveling close to the speed of light, so we can probably just ignore this one. As you can see, light is pretty complicated, so we usually generalize all of this behavior underneath the umbrella term bidirectional scattering distribution function, or BSDF for short, which our BRDF falls underneath. While theory can capture all of this, it's easier said than done because we're limited by our computers. As graphics programmers, we have to compromise on realism based on what we can efficiently compute, and the most important part of it all is the BRDF. So most resources are going to be focused on that, including this video. If you've seen my previous videos, I've already taught you a few BRDFs just without calling them that. So let's do a quick review of those and determine if they are actually solutions to the rendering equation. While it may not be initially obvious to people less familiar with math, this simple equation enforces a set of rules on our solution in order for it to be valid. For instance, the equality operator is doing a lot of heavy lifting. It ensures that our solution does not break the law of conservation of energy. The outgoing light can't be greater than emitted and incoming light. Essentially, we can't produce more energy than was given, as that would break the laws of physics. Another restriction is in the BRDF. It's called bidirectional because the output should be the same if the incoming and outgoing directions are swapped. This is known as the Helmholtz reciprocity principle, which I explained in my last video. These two rules are what we'll check against when verifying our rendering equation solutions. So let's start with the simplest BRDF in the industry. Earlier, I mentioned Lambertian reflectance, but what does that actually mean? From theory, we know that when a light ray collides with a surface, it's going to penetrate it and then get scattered at many angles. For simplicity's sake, we assume that the entry and exit point of the light ray are the same. This is known as a diffuse reflection, when light is scattered all around from the point of intersection. Lambertian reflectance is when the surface diffusely reflects equally in all directions, which is what we're modeling right now as our BRDF, which is still equal to 1. Something else happens when a light ray penetrates a surface though. A certain amount of it is going to be absorbed, never to be seen again, while the diffusely reflected light remains. For instance, if a light ray representing the color white were to collide with an apple, the apple's surface will absorb a large portion of the green and blue light of that ray, while diffusely reflecting the remaining red, giving the apple its red appearance after the reflected light enters our eyes. This is obviously an oversimplification of how light translates to color. For a deeper understanding, refer to my other video on the topic. The RGB color model allows us to represent this mathematically with ease. If the color of the surface is red, then multiplying it against white gives us red, as the green and blue were reduced to 0 per the multiplication. Replacing the red with a variable that describes the base color of the surface, we have derived the most basic of BRDFs, the Lambertian diffuse. Technically, there should be a divide by pi here, but that's usually omitted in most game engine software. If you care about why, you can read this article linked below. The Lambertian diffuse is the most common diffuse BRDF in computer graphics because it's as cheap as you can get. In previous videos, I have shown it with the dot product we discussed earlier, but since it's already present in the rendering equation, we don't need to include it, and we definitely don't want to include it twice. It's named after Johann Lambert, who figured out all of this cosine of the angle stuff back in 1760, but was he actually right? Does the Lambertian diffuse BRDF satisfy the rules of the rendering equation? Since the diffuse color and light color are constant, the only actual variable is the angle of incidence, and we know that cosine cannot output a number greater than 1, so it is not possible for this equation to ever produce more than what was put in, which satisfies the law of conservation of energy. The second rule, requiring the BRDF to have the same result if the output and input directions are swapped, is also satisfied by the Lambertian diffuse, as it does not rely on the output and input directions at all, so it doesn't matter if they're swapped. The output is the same. Congratulations, Lambertian diffuse, you passed the test. You are a solution to the rendering equation, albeit a simple one. With a color texture and normal map, we can already model some ideal diffuse reflectors, such as plaster or unfinished wood, which is why the game I made last video looked decent even though all I was using was this simple BRDF and nothing else. If we try to model something shiny though, like smooth plastic or polished wood, we clearly can't, so we need to add more functionality to our BRDF. Diffuse reflections are just half of the equation. When a light ray hits a surface, not all of it will be absorbed and scattered. A certain amount of it will be directly reflected, which we refer to as...
I might watch the whole thing, but I'm gonna I've just finished eating. But this is like super useful. I think I might actually take notes on this in the future. This is also like it's helping me understand a bunch of stuff, like how the vectors, like this, what is this, the BRDF versus the BSDF? I didn't know that it had all that in it. I just got told it was more complicated. The direction of the vectors, one goes in, one goes out, but to fix the normals, we have to reverse the out, so we get the correct angle, which makes total sense.
as a specular reflection. To make modeling easier, we usually separate diffuse and specular BRDFs, so our Lambertian diffuse is going to stick around while we develop our specular model. Specular highlights are a bit different from diffuse. While diffuse reflectance scatters at many angles, specular reflectance scatters in a much smaller range, so the direction we view the object from actually matters when it comes to seeing these, as well as the light direction. We should only really see specular highlights when the direction of the reflection aligns closely with the view direction, as that's when the reflected light would be mostly bouncing into our eyes rather than somewhere else. So, if we calculate the reflection vector, we could take the dot product with the view direction, which tells us how close together they are, and the result of that is how strong our specular reflection should be. Not all specular highlights are created equal though. Very shiny objects have tiny pinpoint highlights requiring a more perfect reflection alignment to be visible, while other more rough objects have a wider range of specular scattering angles, so we can model this by adding an exponent variable that controls how wide the specular lobe is. This specular BRDF is known as the Phong reflection model and was one of the first models for specular highlights ever invented. Back in the day though, computers were much slower, and calculating the reflection vector—
I forgot I can speak now. Yeah, I don't know slang very well. So I use GLSL still. Anyway.
Was actually a bit costly. If we take a look at our vector diagram, the norm—
But feel free to ask. I mean, I can give it a stab, but you'll find better results likely on the Discord server.
normal vector is also the halfway vector between the light and reflection vectors, so we can optimize the Phong reflection model by calculating the halfway vector between the view and light vectors and taking the dot product between the half vector and the normal vector, removing the need to compute the reflection. This optimization was derived by Jim Blinn in 1977, and the resulting BRDF is known as the Blinn-Phong specular model. Combining Blinn-Phong with the Lambertian diffuse by adding them together gives us what used to be the most common lighting model in video games and other real-time rendering pursuits, because it's extremely cheap and enables us to model a very wide variety of materials in a way that feels physically plausible. Our smooth plastic has the expected specular highlights now, the polished wood actually looks polished, and we could model numerous other materials from shiny to matte, no longer limited to just diffuse reflectors. But is it a solution to the rendering equation? Does it follow the rules? For simplicity, let's take a look at a white surface lit by a white light, since that makes our diffuse BRDF and incoming light equal to 1. The light direction is 45 degrees to the right of the normal vector, and the view direction is 45 degrees to the left of the normal vector, so we'll have a perfect specular reflection. The cosine of the incident angle is about 0.71, and the shininess doesn't matter because 1 to any power is—
I'm sure he does actually. Yeah, it's I might join actually. It might be useful to ask questions on there about this particular stuff.
1. This reduces pretty simply, and we see that the outputted light is 1.42, which is greater than the incoming light received of 1. Unfortunately, the powerhouse Blinn-Phong lighting model of the past is not a proper solution to the rendering equation. It breaks the laws of physics and generates more energy than was received. It's also not bidirectional, so it's not correct to refer to it as a BRDF, but who cares? Just because it breaks the rules, though, doesn't mean it isn't useful. If you're targeting platforms like mobile, where performance matters more than anything, this lighting model is probably good enough for you. Clearly, our simple assumptions of how specular reflections work isn't enough, though, and we're going to need to turn to some more advanced theory from physics and optics to get a more physically correct output. This finally brings us to modern-day physically based rendering, and what everyone else is doing to make their shading models more physically accurate. Physically based rendering is rendering based on physics. The unfortunate reality is that light operates and reflects at a microscopic level, so if we want to be physically accurate with our light predictions, we're going to have to think at that scale. Physics has found it easier to think about the roughness of a surface rather than the shininess metric that we've been using so far. A perfectly smooth surface like a mirror—
Yeah, before I did physically based rendering, just to add like a bit of a caveat to it, I had an engine that did Blinn-Phong, and the shininess was like, it was super difficult to get any type of material into the engine based on just using Blinn-Phong. So yeah, this is a big benefit to moving to physically based.
Is going to look like a flat plane at the microscopic level, but a very rough surface like concrete is going to be composed of microscopic grooves of varying slope and height. The greater the variety, the rougher the surface. These little microscopic surfaces are called microfacets, and they average out to the surface normal we've been using for our model thus far. It's these microfacets that light actually reflects off of, not the average of the microfacets, as that wouldn't make sense. We have a bit of a problem though. Computers can't exactly simulate a near infinite amount of microscopic surfaces to do lighting calculations with, so how can we model something that can't actually be modeled? With statistics, of course. If we assume these microfacets are perfect mirrors, and we know from the Blin-Fong lighting model that the direction of perfect reflectance is the halfway vector between the outgoing vector and light vector, then we can model the roughness of our surface as the probability that the light hits a microfacet that points in the direction of perfect reflectance. In other words, what is the distribution of microfacets with a micronormal equal to that of the halfway vector between the light and view vectors? This could be any distribution function we want, so we'll declare it as a generic one for now. The next term of the microfacet model is the Fresnel equations, which describe a phenomenon in which surfaces demonstrate greater reflectivity when viewed at grazing angles. For instance, the hallway floor becomes more mirror-like towards the distance as the angle of incidence decreases, and another popular example is the ocean specular. Abstractly, the Fresnel term describes how much light is reflected based off the view angle, which can be any function we want, so we'll declare it as a generic one for now. Lastly, the microfacet model includes a geometric attenuation term, which accounts for the scenario in which microfacets can block each other, reducing the chance of a reflection and causing a phenomenon known as off-specular peak, where the peak reflectance is achieved at a lower angle than otherwise predicted by the Fresnel term. Essentially, the geometric attenuation term counteracts the Fresnel for very rough surfaces. This can be any function we want, so we'll declare it as a generic one for now. These three abstract terms are multiplied with each other and divided by this denominator. Why is this the denominator? Because it's what the most recent literature agrees on. This completes the microfacet BRDF for specular highlights. When we say something is physically based, that means it's derived from microfacet theory. Physically based rendering doesn't always mean photorealistic rendering though, because remember that these functions can be anything we want. They don't necessarily have to follow the...
Never mind. Yes. I struggled to say that one. Yeah. Schlick.
real world, it just has to follow the model. As it turns out, Disney derived their BRDF from microfacet theory, so let's finally take a look at how Disney solved the rendering equation. Okay, I lied earlier when I said Disney uses this to model every surface in their movies. They use it for every surface except hair, because hair is just too complicated and deserves its own model. Still, there's enough versatility and value here that Brent Burley presented his team's process for developing their new BRDF model in his SIGGRAPH 2012 talk, Physically Based Shading at Disney. For transparency, this is not the most recent version of their shading model. The one we're about to discuss was extended for Moana and beyond, and the talk going over that was in 2015 by Brent Burley again, discussing the extension of the BRDF into a BSDF to support subsurface scattering. That is beyond the scope of this video though, so we'll put our focus on the foundation for today. Burley's presentation discusses the initial research and design philosophy behind Disney's BRDF, such as the guidelines for each parameter of the shader, and most notably how they fiercely debated the addition of each parameter and the pursuit of having as few settings as possible, which is funny to me because I have the opposite design philosophy. The end model has 11 parameters that control the appearance of the surface, but listing them all out would be kind of pointless, so let's start from the top and build the model piece by piece. The first parameter is the color of the surface. If you remember from earlier, this is part of the diffuse lobe, but does Disney also use the Lambertian BRDF? No, they use a different model for diffuse reflections invented by Brent Burley, known as the Burley diffuse or the Disney diffuse. The Disney diffuse is an extension of the Lambertian model that takes into account Fresnel reflectance, which is dependent on the second parameter of the Disney BRDF, surface roughness. Fresnel reflectance in physics is described by the Fresnel equations, which are extremely complicated, so complicated that Natty Hoffman wrote a paper called Fresnel Equations Considered Harmful. The paper concludes means that it's a waste of time to use these Fresnel equations in most rendering contexts, and the only benefit would be seen in spectral rendering, which we aren't doing. So instead, we will go with a simpler approximation. The Fresnel approximation everyone uses was invented by Christoph Schlick in 1994, which models how materials exhibit perfect reflectance when viewed at or under 90 degrees. Essentially, the Schlick-Fresnel interpolates from the base reflectance a surface exhibits to the maximum reflectance a surface exhibits based on the incident angle. The Disney diffuse calculates the reflectance at 90 degrees from the roughness parameter, and the angle between the light and half vector, sets the base diffuse reflectance to max, and then calculates the Fresnel based on the angles of incidence from the light and view directions. This is then multiplied with the base surface color, since it's diffused light, and divided by pi. I chose to include the pi this time because I think it looks better. When compared with the Lambertian BRDF, the difference is quite clear. A roughness of 1 makes the sphere look brighter on grazing angles, while a roughness of 0 has the opposite effect because a smoother surface will diffuse less light. Is the Disney diffuse a solution to the rendering equation? Does it follow the rules? No, it fails to conserve energy, which means that the entire Disney BRDF will not follow the rules. But who cares? Remember that the goal is creative control with physical plausibility, not photorealism. The next parameter of the Disney BRDF is subsurface scattering. But Acerola, you said this version doesn't have subsurface scattering. It doesn't. The Disney BRDF provides a secondary diffuse lobe for artists that is an approximation of the Hanner-Hahn-Kruger subsurface BRDF, which effectively flattens the diffuse reflectance and makes it look more uniform across the surface, but it is not a replacement for genuine subsurface scattering, as you can see that the diffuse does not blend into and illuminate shaded areas like genuine subsurface scattering would. The subsurface parameter blends between the Disney diffuse and the subsurface scattering approximation, allowing for more artistic control. The next parameter is the sheen strength, which is an additive lobe based on the angle between the light and half vector, such that when the light is at very grazing angles, there is a slight sheen to the surface, observed on materials like cloth. There is no physical basis for this, it's just an additional artistic parameter, which is accompanied by another parameter that tints the sheen towards the color of the surface. This completes the diffuse portion of Disney's principled BRDF. You can already see how there's way more creative control here than there was with the basic Lambertian diffuse, even if it's not exactly physically accurate. Now it's time to look at the specular portion, which is the cooler part. While the diffuse lobe did not make use of the microfacet model and instead extended the Lambertian diffuse, the specular lobe does derive from microfacet theory. Remember that this means we have 3 individual components that need to be solved: the microfacet distribution function, the Fresnel response, and the geometric attenuation factor. Let's start with the distribution function. There are lots and lots of existing distribution functions to choose from. The 2 most popular are Beckman and GGX, with GGX being most commonly used today due to people saying it looks more physically accurate than Beckman. If you recall from earlier, the distribution function describes the fraction of microfacets that are oriented in the direction of perfect reflection, and this is dependent on the roughness of the surface as well as the angle between the half vector and surface normal. This graph of the distributions shows how much light can be reflected based on how different the half vector is from the surface normal. Remember that the half vector is the direction of perfect reflection, and the surface normal is the average orientation of the microfacets. So this function models how light is more likely to be reflected when the average direction aligns with the ideal direction. As you can see, GGX and Beckman distribution have a similar peak, but GGX sharply falls off and then slowly fades, while Beckman behaves in the almost opposite way, with the distribution actually reaching 0, which GGX never does. There is always at least a little light that's reflected. Disney chose to use GGX for their primary specular lobe, and once we visualize it on our sphere, we get a better idea of how it's working. White corresponds to a full reflection, while black corresponds to no reflection. At a low roughness value, it means we have a smoother surface, and so light is going to more perfectly reflect off of it, resulting in tighter but brighter specular highlights, while a high roughness value flattens out the distribution, resulting in a wider scattering range and a dimmed specular due to less light being perfectly reflected into our eyes. This is when the next parameter of the Disney BRDF comes in, as Disney makes use of the anisotropic version of GGX space in order to support anisotropic specular highlights. Anisotropic means that the distribution is not square and varies based on the axis, which when applied to specular highlights results in elliptical speculars rather than the circular pattern you're familiar with. Many surfaces in the real world demonstrate an anisotropic specular response, your own hair being an example, as well as stuff like brushed metals, so this parameter allows for more surfaces to be modeled, as well as provide more creative control over the shape of the specular. The distribution term is the most impactful part, as it's mostly responsible for driving the shape of the specular highlights, but we still need the Fresnel and geometric attenuation term to finish the reflections. The next parameter of the Disney BRDF is the specular strength, which describes the base reflectance of the Fresnel approximation we discussed earlier. Since Fresnel only uses the angle between the light and half vector and doesn't care about the actual surface normal, it looks a little weird when we visualize it on the sphere. It's easier when we look at it on a plane. Remember that brighter pixels means a stronger reflection. Lastly, we have the geometric attenuation term, which counteracts the Fresnel by modeling how microfacets can block and shadow each other, preventing rougher surfaces from demonstrating high reflectance at grazing angles. The attenuation consists of two parts: shadowing, when a microfacet blocks incoming light, and masking, when a microfacet blocks reflected light. Thankfully, the two parts are the same function, just with different inputs. Conceptually, the geometric attenuation function describes the geometry of the microfacets themselves, and the main model for that is the Smith model, which treats the microfacets as a randomized distribution of slopes. Unfortunately, it relies on a specific function derived from the distribution function, but thankfully we already have solutions for the common distributions like GGX and its anisotropic counterpart. Visualized on the sphere, we can see where the geometric attenuation will dim the brightness of the speculars to account for shadowing and masking, with a more uniform dimming at higher roughness values. Now, finally, we multiply each of these together, divide by the microfacet model denominator, and we get our beautiful specular highlights. Of course, we have to add the result to the diffuse BRDF to see both of them in action. This already looks pretty good, but we still have 3 shader parameters left of the Disney BRDF, with the next being the metallicness of the surface. We haven't really talked about metals this video, but unfortunately, they have their own unique behavior when it comes to light interaction. As mentioned earlier, many metals exhibit anisotropic speculars, which our model accommodates for already, but some metals are also known as dielectric, which means they tint the specular reflections towards a certain color, just like how diffuse reflectance tints colors. Lastly, polished metals do not diffuse light, only reflect it. In order to accommodate for the other behaviors of metallic materials, we want our metallic parameter to reduce the diffuse contribution to 0, as well as tint the color of our specular towards the base color. Now we can model metallic materials like gold and silver foil. Our last 2 parameters of the Disney BRDF are for a second artistic specular lobe called the clear coat layer. Essentially, we do all of that specular stuff again, but Disney uses the isotropic GGX distribution for simplicity. The clear coat parameter controls the strength of the lobe, and the gloss parameter controls the roughness of the distribution. The diffuse lobe, specular lobe, and clear coat lobe come together to form Disney's principled BRDF. With this, they modeled every single surface, except hair, in movies like Wreck-It Ralph and beyond. It looks kind of bad sitting in this black void though, so let's put it into a new environment to see what it's capable of. Adding a few lights in a skybox helps quite a bit, but remember that the BRDF is only one half of the lighting puzzle, and it must be paired with a sufficient light transport algorithm to solve the indefinite integral of the rendering equation. In the case of Disney, they get to do path tracing for indirect lighting and global illumination. Unfortunately, we do not get to do that because I am focusing on the real-time rendering context. This means we have to sort of fake indirect lighting, which I did by sampling the skybox from the direction of the surface normal and then using that as the lighting input for the Disney BRDF, which gives us some simple indirect diffuse and specular highlights to make the sphere fit in more with the environment. I created a few different materials and substance to demonstrate how the BRDF can model very different surfaces, such as dry mud, wet mud, wood, flesh, denim, and metal foil. I put together a little material editor where you can play around with all of the shader parameters, material texture sets, and lights, which you can find over on my Patreon. As usual, a huge thank you to all my patrons. Without your support, I wouldn't be able to spend 10 days straight editing this video. In the end, even though Disney's lighting model breaks the rules and fails to solve the rendering equation, it's still physically based because it's derived from microfacet theory. I hope this has communicated how math comes together like little Legos to produce grander, more sophisticated models that can encapsulate many things at once. Since it's not real, we can make any amount of creative adjustments for more artistic control.
Makes
or
sense.
we can abide by the rules to get a more photorealistic result. But at the end of the day, high-fidelity games like Horizon Forbidden West and God of War Ragnarok, which also make use of microfacet theory, are just a few creative decisions and lever pulls away from looking like Disney movies, and that there isn't as much of a difference between them as you'd think. I often hear the sentiment that people don't care for the high fidelity photorealistic graphics anymore, but just remember that it's through that high fidelity that we get more interesting stylized graphics. All it takes is for someone like you to invent it. Anyways, that's all from me. I hope you have a great rest of your day, and I'll see you next time.
There we go. I hope you guys enjoyed that watch along. That was really useful because we're going to actually debug my normals when it comes to working out the direction of the light source that's coming in for the my BRDF. My BRDF is wrong, so we're gonna have to dig into those three individual parts of that function and just see which way the reflectance algorithms work. So I'm just gonna clean up. I will be, again, sorry to disappear twice, but yes, so that's what we're going to do. We're going to do a little bit more studying, but not much more. And then we're going to go into game dev, right? And hopefully fix some of the basic lighting issues that I have. I'm just going to, all I'm going to do is just move some of my stuff away. So hopefully that's all chill beans. Yeah, give this guy a sub if you haven't already. Look, I'm already subbed. He's, I've been subbed for a long time. I just actually haven't watched this one for some reason. Must have been one of his older ones. When was this made? 2 years ago. Okay, maybe not. Alright, so yeah, I'll be right back to you when I've moved all my stuff from where I am. Alright, see you in a minute. Alright guys, back. So thank you for bearing with me over that much time. Yep, okay, so let's get back into it. So like I said, a bit of studying, probably going to stop at about 2:30, which is about half an hour-ish. We'll see, I'll see what a good breaking off point would be. So actually, let's remove some time from that. That didn't happen. Probably, let's get rid of 5 minutes. Okay, so, right. Hopefully the music's all good. It's not too loud. I think that's the average. No, it seems extremely quiet. Okay, there we go. So that hopefully should be good for you guys. Yeah, so let's dive back into it, hey? Improving efficiency. There's so much stuff I just do not know. It's I wish I just knew everything about this. Because a lot of what I've been learning, let's go to these, don't save, is unfortunately just ray tracing and path tracing stuff. And you know, estimating It almost makes me think like, am I on the wrong book? But I think this is still going to be useful in the long run. Should I be reading physically? What is it? Real-time rendering instead. But anyway, I'm not gonna worry about it. Worrying about it would Alright, so let's just close a bunch of stuff. Just so we don't end up yeah. Alright, so oh, that was the thing I need to do. So what we're gonna do is split everything up. So we have background and review and probability. Background and probability review. Alright, so yeah, this is the this is ray tracing, but it's like kind of maths-y. I almost need like a Monte Carlo thing, but should I add another tag? This is more maths than anything. Do I have a maths tag? No. Yeah, okay, I'm gonna make a maths tag, I think. So the idea is just to organize data, organize notes. Because this isn't ray tracing really, it's just a bunch of maths. Which unfortunately goes on and on and on, but that's just the way it is. You just copy paste it, nothing. Copy, paste. Yeah, so this is 800 words. I was tempted to split this up. But it kind of needs to be all in one place, because otherwise it doesn't make as much sense. Yeah, so I am going to obviously connect this to the Monte Carlo. Maybe a probability tag. Yeah, that's probably a good idea actually. We'll go with maths for now, and if there's more maths, then maybe probabilities is its own thing. Yeah, because I can always categorize the different things. So, all right. Yeah, there's so much I don't know when it comes to Okay, so where should I put this? This is I don't think this is part of ray tracing at all. This is just the maths section of graphics theory, which is just pure maths. So this would be, you know, if I didn't know how like cross products work in vectors or something. So if there's any more maths related stuff, then we can put that in there. Okay, so, and fortunately I don't have to read any of this because we read this earlier today. So expected values, this is just also just maths, but it's also, yeah, okay, so expected values, which is just more probability really. So expected values. Probably a link to the R. Probably a link from ray tracing. But not the other way, right? Yeah, I'll do that. This will all be linked together as well. It's often starting out, it's one of these things where it's like the links themselves are really weak at the beginning, but then they get like stronger. So it's like now we have the background improbability, for example, and then we can link this in the next part. So these all have, oops, connections like this, and so these are good. They're pretty hefty chapters, but yeah. So reducing errors in Monte Carlo. Oops, have I copied two? Oh, I have. Okay. I've copied too much here. So with the Monte Carlo stuff, I think that is definitely ray tracing. Whoops. Whoops. Okay, so fantastic. Yeah, we don't want to add too much. Reducing errors in Monte Carlo. Yeah, doop. Put that there. I hope it we get the bidirectional reflectance distribution function rather than just the BSDF, because I don't know how realistic is it that we can, even without ray tracing, produce the the bidirectional scattering distribution function. It's kind of like something I'm just a bit concerned about now. Because if I, oops, let's throw these together. Expected value, definitely need to know this. And then this needs to be in here. No, expected value. Yeah, it just worries me a bit that I'm learning stuff that will never be useful in real-time rendering. Well, we don't know yet. I mean, obviously, all of this is going to be useful eventually. Okay, so we need the maths, expected values. Because the goal isn't to understand how to do ray tracing, it's understand how to do how physically based rendering works, which is going to be useful if I learn it through BSDF or BRDF, or heaven forbid BSSDF, which is even more accurate, but obviously way like 7 times, 8 times more expensive than BRDF, because we're doing a lot more. No effort wasted. Yeah. I think I think all this is gonna be valuable, but it does worry me that I'm well, at the very least, I understand the rendering equation. Better. Which is good, and I think it's safe to say that I've got slightly better at maths, which is just generally good in general when it comes to graphics. The stronger you are at maths, the easier time you have. So absolutely no wasted effort really. It's just you know, the speed at which I get to my goal is affected by what I end up learning. I love the fact these are auspicious. It's so nice to have. So we need expected values in here. More holistic approach will make it more intuitive. Yeah. That's a good point, actually. Yeah. So rather than targeting, because there's, I guess I'm coming from like a top-down perspective when I'm learning it. My goal is to be able to obviously render nice things, but you know, if I just learn like the GDX, like how to do GDX of the BRDF when I'm using that particular model, I won't get a whole holistic understanding of things. Expected values, and we need to reducing errors, which, you know, errors in multicolor. And overall, this is absolutely fascinating. Like, I'm enjoying the learning process so much, to be honest, that it almost feels like I could temporarily. I think it would eventually not. I always want to create stuff. I feel like I've got a creative drive in me. Excuse me. This is a bloody fly. Sorry, I keep. It's a fly attacking my face. What was I saying? So yeah, this is super fascinating, all this stuff. I just want to make sure that I actually make something in the end. So I'm enjoying this. That's the comparing accumulators, comparing estimators. Yeah, they're gone. Yeah, the fly's gone. I got it in the end. It's like a little gnat, you know. Or is that not what you were talking about? Sorry. Estimators. Alright. But I think all I have to do literally is just code my engine and not just go down the rabbit hole and study all day. And I think I'll be okay. And ray tracing. Because this is going to be useful if I actually do want to do ray tracing, which may be a thing that I end up implementing. And path tracing. But that's likely an offline job. What do I want to grab? Errors in Monte Carlo. So we need a reducing errors. Now give me a background on what the estimators are. And what else do we use mathematically in here? Expected values, so we need variance, which I believe is here. Yep, okay, so these are all good. Yeah, we use expected values, so these need to be in here as well. And anything else? No, I don't think so. Okay, comparing estimators. Oops. And the final one, I believe, is a bit of a crazy title, but nope. Need to make a new tab, sorry. And paste that in. Let's grab our work that we did. Let's rename these to EST capital. Easier to read. Right, okay, so obviously this is to do with comparing. So we need this to connect to it, and we need the source, which is physically based rendering. At the very least, if I understand this, my understanding of physically based rendering will be so good that in 20 years, when inevitably we move to BSDF for real-time rendering instead of BRDF, when it comes to solving the equation, the rendering equation, I'll at least know how to do it. Whereas like a lot. Ooh, I've included 2 things in here which I don't need to. Biased accumulators. That's a separate note. I'm thinking these are bigger than they are, but I guess not. So bias. Estimators. Okay, so that goes in here instead. So this needs to be connected up to everything. Graphics theory. Oh, and the music stopped. Ray tracing again. Okay. Let's quickly pick something for listening. I am going to go with just some Skyrim stuff. How's that sound? Hi Mohammed, good to see you again. I'll just read what you said in a moment. Just let me type this out. So these need to be connected with estimating accumulant is 100%. Nope. Sorry. Get rid of this. Huh. I think I've messed up here. You need to be laser focused on what you're learning and doing, because there is a match. There is so much cool stuff out there. Yeah, 100%. You're not wrong there, Mohammed. I will keep on with my studies and work as hard as I can for it. That's why I'm drilling this to death, rather than because I think there's a danger. Okay, so I think this might be relevant for people who are new, but also this is a good reminder for myself, by the way. This is not just for new people. There's a danger when it comes to learning things, that you hop from thing to thing to thing over and over again. That's the bias. Where did I put the bias twice? And you can end up in this bad situation where, yeah, I guess this needs to be connected to this, where you would have been fine, you know, sticking to one thing for long enough for it to become useful. But because you've hopped from thing to thing to thing over and over again, you end up, you know, taking longer than you would have needed to. And it's one of those things where it's like, I could, you know, now I've kind of watched that BRDF video. I'm like, oh, I didn't understand some of that when I maybe should have. But what's going to end up happening if I leave this resource behind is I'm not going to get the stuff out of it that it's offering, and I'll always just have a shallow understanding of like rendering, I guess, in general. Because in this hypothetical example where I just keep hopping from thing to thing to thing, I never go deep enough to actually get the full picture. And it is a bit of a trap. So yeah, you have to be aware of that when you're thinking about what you should and shouldn't learn. A lot of the time, it's like if you just stick at something for six months, like you'll thank yourself that you did that. And that's what I think when I think about these type of things. Yeah, it's a huge field, and I think even if I learn, let's just say, just ray tracing, if I take it all the way to like its conclusion when it comes to a particular resource, I'm probably just going to be a better programmer than if I were to take, say, read the first chapter of, 40 books or something silly. Yeah, that's an extreme example, but that's what you can end up doing when it comes to. It's like there's like this thing when this almost comes from weightlifting, right? People who are like new to weightlifting, they'll be like, oh, what's the best? They'll say, what's the best resource for weightlifting? And you'll be like, oh, just follow this program, and you'll be fine. And then you'll like hear about another program, and they'll hop from that, and then they'll figure out like, oh, maybe I could eat this particular way, and they hop their program again, and then they're like, oh, I actually want to do strength training. I don't know why I started doing bodybuilding. I'm gonna go back to strength training again. I don't know. I feel like doing cardio now. I'm gonna start like learning to run. Oh, but that's making me so. Oh no, now I'm weak. Now I'm a little weaker in my strength, so I need to do my strength training again. Like, what ends up happening is you end up like making no progress because you end up like jumping from thing to thing to thing over and over again. So it's like that when it comes to I think what I should be studying. Okay, so we don't need this. I think we're pretty good. I just need to kind of get everything together. So the Monte Carlo estimator, the areas of Monte Carlo, biased, you know. Let's put that there, and this is the bottom. Whoops! Whoa, 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 whoa! Knocked my thing then. Areas in Monte Carlo, we got that. Expected values. I think I'm done with this. What do I need to understand here to be able to do this? I guess I would put the Monte Carlo estimator at least, because now we know there's an example of an estimator. And then I think I'm done. Okay, there we go. Detri, I'm working on a little 2D fan game right now, and it's nice to rest my brain from thinking too hard about buffers and algorithms. Lol. Yeah, it's I can see the benefit of doing that. Yeah, I hope that's going well. I hope you're enjoying yourself with that that fan game, whatever that may be. Okay, just make sure. Okay, so we've got estimators, comparing, and yep. Let's just go from the top. I think I've missed one. You see, that's all. That's the Monte Carlo estimator. There's errors in Monte Carlo. Yeah, I'm missing something here. Comparing errors in Monte Carlo. Reducing errors in Monte Carlo. Yeah, that's what I've missed. I think. Because I think I included this in one. Yeah. We'll see anyway. It'll come up if I've already written it. No, okay, I hadn't written it. Yeah, I knew I'd missed one. So let me just grab this. So we need the breaking down the transport light equation. Ray tracing, and then we need errors and blah blah blah. We definitely need this one, and we need the at the very least. Do you have expected values? Nope. We need the Monte Carlo estimator, and then that's at the very least that's what we need connected. Okay. We got that done. Throw this in. Yes, I knew I'd missed one. Okay. And let's just for fun look at my graph thing, eh? So that should be graphics theory. It's getting pretty chunky. And there's ray tracing. So yes, very nice. Very nice. This is Vulkan, if you're wondering. Okay, bit of fun. Yeah, performance, threading, C++, operating systems assembly, and just C++. Beautiful node graph. Looks like this graph. In theory, this is what my knowledge should be, right? It's like all my ideas should be connecting to each other. Look at this graph, yeah, elite ball meme. Look at this graph. I gotta be careful I don't get copyright striked with my excellent singing voice. Alright, so we need to continue. Unfortunately, I all of a sudden need the toilets, which is quite annoying. So, I will, now I've done that, pause this, and yes, I will be right back. I was thinking, wow, I don't need the toilets, and then when I was putting stuff away. And yes, I was wrong. Never mind. Sounded on pitch to me. There we go. Uh-oh. Be right back. I'm getting better at climbing over this chair. You never know. All that time in the gym's paid off. I can now climb over a chair. Anyway. Right, improving efficiency 2.2. Alright, let's restart this. I don't know why we zoomed in here, but let's fix that. Do this, and let's continue on note clicking. Okay. So I assume that we don't probably need to take our own out on the introduction, but actually I'm gonna introduction on improving efficiency for ray tracing, I think. No, for Monte Carlo. Alright. And put that there. Okay. Okay. So yes, I'll because I didn't realize like how much time I've eaten away. I'm gonna probably study for a little bit longer, not much more. I said I was gonna finish at 2:30, but maybe 3:30, maybe 3, something like that. Okay, so improving efficiency. Given an unbiased Monte Carlo estimator, we are in a fortunate position of having a reliable relationship between the number of samples taken and the variance, and thus error. If we have an unacceptable noisy rendered image, increasing the number of samples will reduce errors in a predictable way, and given enough computation, an image of sufficient quality can be generated. However, computation takes time, and often there is not enough of it. The deadline for a movie may be at hand, or the 16th of a second time slice in a real-time renderer may be coming to an end. Okay, yeah. So it talks about real-time rendering. So we're not completely dead in the water here. With this is only used for offline rendering. Given the consequential limit of the number of samples, the only option for variant reduction is to find ways to make more of the samples that have been taken. Fortunately, a variety of techniques have been developed to improve the basic Monte Carlo estimator by making the most of the samples that are taken. Here, we'll discuss the most important ones that are used in a PBRT. There we go. There we go. Okay, so yes, you can use a straightforward Monte Carlo estimator, and with enough computation time you should get a clean image generated. However, ain't nobody got time for that. So when we talk about efficiency, in Monte Carlo, we are trying to make more use of the samples we have taken. Alright. Oh, I might have actually. Did I not send it out? Here's where I pressed. Oh my goodness. Yes, thank you, Ratchet. Sorry. I was a bit distracted, admittedly. Sorry about that, guys. I've sent it out now. I know it's a bit late. Yes, thank you. Sorry about that. Yes, you are right. I should have sent out. Thank you. I'll look at my. I'll be like, oh, why were less people watching my live stream? It's all my fault. Yes, thank you for that. Okay, so just to catch everyone up who may have just joined, we have done revision. We are coming to the end. Well, we have finished a lot of the Monte Carlo basics. Now we have to figure out how to increase the sampling speed for our Monte Carlo estimator. It turns out in the world of estimators, there is a variance that we need to worry about. But, funnily enough, you need to basically use random variables to sample over the variance of the errors that happen in the Monte Carlo estimator to work out the integral in the rendering equation. So that means you need to estimate the variance of the Monte Carlo that works out the integral of the rendering equation. So that is what I've been learning about recently. We have random numbers sampled all the way down. Very cool. And now we're figuring out how to speed up and use our samples better. With looks like set theory, but here we are. So I'm going to read from this. So we will get to coding soon, though. Probably about at the very most an hour. 2.2.1 stratified sampling. A classic and effective family of techniques are for variance reduction. So variance, for the people who have just joined, is the error in which the Monte Carlo estimator is from the integral if we solve the integral analytically. So in the rendering equation, we have to consider all light sources that come in over a hemisphere for a particular point. That's what the integral's for, right? And obviously we can't do that, but when we send in random values to this integral, and we figure out what the if we input this random vector, which would just be a light direction, and we get something out, we are going to have variance based on an error. We're going to have some error based on the analytical actual solution and the what is it called? The Monte Carlo guesstimate, estimate that we actually got out. So we are here trying to figure out how to increase the sampling quality, right? So we do ray tracing based on sampling per pixels, and yes, we could just sit here and just spend thousands of hours rendering the perfect image. Well, that's a bit of an exaggeration, but there's not enough computation, and we want to render a nice image. How do we take advantage of the samples rather than just spending more computation time and asking people to move up the upgrade their graphics cards, right? Space Game Duck Edition RTX, exactly. So this is all with the motivation in mind that I will eventually get to a point in this book where I don't have to worry about ray tracing anymore, and I can actually really dive into all the lighting that comes with physically based things. This may be not a mistake, but this may be a top-down approach where I have to read this book, understand physically based rendering, and then also read a book like real-time rendering to then move whatever was here into a real-time rendering context. We'll see. The only way to find that out is by reading further into this book. And that's what we were just discussing earlier, because you can get into a mindset where... Sorry, I'm rambling so much, I should pause the timer. Not rambling, but I think it's good to know. There is a temptation to switch resources to make sure that I'm doing the absolute right thing, but just like with weightlifting, there's a lot of... when you get into weightlifting, or if you get into weightlifting and working out, there's this idea that sticking to a particular program, even if it's not the optimal approach, is the best approach, because there's this temptation that beginners have, or intermediates, or even advanced people, really, so people in general, to constantly hop programs. And the problem with that is the weightlifting programs that do a specific thing like bodybuilding or build strength are designed to be taken over maybe 5+ years. Typically it's like they're designed for a long period of time, and if you just keep switching from program to program, you end up in a bad situation. You end up like not progressing as you would. This is my justification of why, despite that this working out the mean square error for an estimator might be not useful in the long term when it comes to real-time rendering with raster graphics. It's going to be better if I stick to one resource and really drill into it rather than get worried and like hop from one resource to another. That is my approach and opinion on this. So yeah. Anyway, it's just to fill you all guys in on that. Yeah, I think I said that earlier, but for the people who've just come in, anyway, a classic and effective family of techniques for variance reduction is based on careful placement of samples in order to better capture the features of the integrand. It makes sense. Or more accurately, to be less likely to miss important features. Okay. Oops. To improve one idea to work to improve efficiency. When it comes to reduce variance is to worry about the placement of the samples to better capture the intergrand aka miss not missing important features. Okay. These techniques are used extensively in PBRT. Stratified sampling decomposes the integrand domain into regions and places samples in each one. So what does this mean exactly? I just want to clarify my term exactly here. Arranged in sequence. Okay. Okay, so when we say arranged, sorry, stratified, we are really talking about the arrangements of the samples. Okay, so stratifying samples, oops, into domains decomposes and into domains integration. Let me just write it out, kind of like they did. Stratifying, just because I want to use my terms correctly here. Sampling decomposes the integrand integration domain into regions and places samples in each one. Nice. Okay, later in section 8.2.1 we will return with machinery based on Fourier analysis that provides further insight. Machinery based on Fourier analysis. Sounds intimidating. Okay, so stratified sampling subdivides the integration domain into, what is that? An alpha, maybe? Domain this into n non-overlapping regions, alpha 1, alpha 2, alpha 3. Each region is called a stratum. Ah, I see. And they completely cover the original domain. Okay. The ultimate technique, domain correction. Yeah, that'll be my super. That'll be my what is it? Cursed. I can't remember what the. I know what you're talking about. You're talking about domain expansion. Yeah. With curse techniques. Oh. Yeah, it's gonna be the Gojo or whatever his name is. Anyway, all right, so stratified sampling subdivides. Yeah, what's John Vulkan's domain expansion? Maybe he's able to correctly handle the swap chain. That's it. Domain expansion. I can resize the window on every platform. Holy, he's done it. He's gone ultra instinct. Yeah, domain expansion, swap chain resize. Damn. There it is. Okay, so stratifying sampling subdomains, integration domains. So stratifying sampling subdivides the integration domain. Okay, I think this is fine if I just mostly type this out, but let's see how you. Is this just alpha with a capital A? Oops. Alpha. Nope. That's how you spell alpha? LaTeX symbols. Oops. Let's see. Hopefully this just tells me everything. Yes. I need to not close this. No. Okay, alpha's just A. We want to make a weird A without a thing. Which I'm sure our stratums are probably represented by this letter thing. This is logic operators, which we're probably going to have to use. And oh, it's overline. That's what I needed to do. Okay. Interesting. Where is this symbol? It must exist. Aleph. Don't need the. We're not dealing with infinity, so we don't need them. Right, I'm just gonna be a bit careful here because I probably went past it. Okay, so there's cup and cap. Ah, okay, wedge, maybe. Let's see. And if I go back to the book, no, it's not quite reg. But it'll have to do if I can't find it. Just a bit more searching. This is kind of a... I don't think I'll ever use the wedge product in ray tracing, but let's just make sure it's not a Greek letter, just real quick. Oh, it is. It's lambda. It's capital lambda. It's just capital lambda. Okay, there it is. Found it. It's just capital lambda. Fantastic. Okay. Okay, so into n non overlapping regions. That's all added together. Called stratums. And they complete the original domain expansion of John Vulkan that he can resize the swap chain. Okay, so let's see, cop, right? And then we go underscore I equals 1. Oh, how do I do that then? To be honest, I have no idea what you're working on. I'm just staring at code, hoping for some inspiration. Yeah, it's I feel like I've gone down like the biggest rabbit hole of all time when it comes to ray tracing. I'm figuring out how where's the sets then? How do you speed up the Monte Carlo algorithms, which may be akin to learning how the rasterizer works when you don't even have access to the rasterizer when it comes to Vulkan. But yeah, I'm just gonna roll with it. Because you know, no knowledge is really wasted. Where's the? Ugh. Oh, maybe. Hang on. Maybe I'm being stupid. Maybe it just tells me. Union. Is there a union in here? Set union. No. Okay, so that's just how we're gonna have to write it like that. Okay. I don't know how they've written it, but I think you misread that, mate. I was talking about myself. Oh. To be honest, I have no idea what to work on. Oh, you have no idea what to work on. Okay. My bad. Yes, I I did misread. Did misread. Did misread. There we go. Lamb. I have a lambda. Copied and pasted last time. Lambda. Okay. Lambda. Okay, so we're just gonna have to write it like this. Backslash lam. Oops, capital A. It looks like a capital A to me without the cross. I wish that was. I wish I could write it like that, but yeah, never mind. Anyway, to draw samples from lambda, we will next n samples from. Ah, yeah, no problem. No problem, Ratchet. I hope you do find inspiration. Out of curiosity, do you have to worry about stratifying your samples when it comes to ray tracing? Because I know you've done ray tracing, so I haven't actually put it in into Vulkan. Like, do you like have to think about like cleverly how you will be sampling when you when you start ray tracing it with RT hardware? It'd be good to know. If you don't, then also don't worry about it. Anyway, to draw samples, there should be. I just can't find it. There's the I use union twice. Set union. Ah, big cup maybe. Okay. Oops. Oh, thank you. Perfect. I only have hard shadows, so 1 ray per pixel. I see. And I'm rasterizing the primary visuals anyway. Ah, I see. you didn't even look that up. Oh, there we go. TT's got some foresight. What the heck? Yeah, that was actually it. That was actually without the underscore, but yeah, pretty much it. Yeah. I just trust you, TT, so much that I just assume that you just know everything. There we go. Same with Ratchet, to be honest. Okay, so let's actually chew on with this. Okay, so to draw samples from the, I'm going to just select lambda, we will draw n underscore samples from each stratum according to the density p, which I assume is what? Inside each, pixels, inside each pattern, inside each stratum. Okay, so to draw samples from slash lambda oops in n underscore stratums with pixel density of pi yes, it's on GitHub, but it's yes, let me I haven't been to do this all day, so I'll do it now because 2 people have asked me about this. So I'm just going to push up my notes if you actually do want to look at my notes. You will have to use a tool called Obsidian. That would probably be the best way to view it, but if you do, you just point the vault at this what is it called? Because they're just all .md files. So .md .md, these are all my notes on various things. So to actually organize that, I use a tool called Obsidian, which helps me like render everything. But anyway, I will actually just, because this is publicly available. I made it publicly available because back when I was working, I didn't want to have to justify to my company that I was pulling from a private repository. Anyway, so added a ton of graphics theory, and then push. I'll take probably a few seconds. Yeah, so this is on my GitHub under Obsidian notes. So if you go to my GitHub and you're interested, you should. These are my game engines, but if you find in my repository list, like here, and look for Obsidian notes, then you should be able to find my notes that I'm writing. I'm writing only for this particular engine here is the reason I'm doing that. But anyway, there you go. Hopefully that's useful if people are interested. I do need to commit every now and again anyway, so that's just useful to do. Yeah, no problem. But I do recommend if you do want to read my notes, these are more. Yes, I feel like I've done well with my notes, but I think it would benefit people to make their own, but feel free to nab mine. There's no reason not to. I only say that's not because I don't want you to use mine. You can use mine. Anyone can use mine. It's all public for a reason. But I feel like you would be, it would help you learn better. That's all. That's the only reason I say that. I had software shadows. I did multiple rays per pixel with random offsets and averaged them. Did some some kind of temporal thing, I'll just say. I don't know what that is. Interpolation. Nice. Denoising. Okay. Strata. Okay, so yeah, I could probably use... It said stratum, right? Each region is called a stratum. Is it really not strata? I don't know. Maybe the book's got it wrong. Okay, anyway. Inside each stratum. For each stratum. I feel like with 4K monitors as well, like ray tracing must get like 100 times more expensive. Anyway, with a sample is an example of a superpixel, a super sampling a pixel. Each stratum, each stratified sampling, with stratified sampling, the area around the pixels is divided into a KXK grid and is drawn uniformly within each grid cell. Thankfully I have a 1080p monitor, yeah. Same here, to be fair. But I feel like if I released a game with ray tracing and someone had a 4K monitor and we were like, why is the frame rate 15 frames per second? It would be assuming that the resolution is 4K. Might get some negative feedback on that one. With stratified sampling, the area around each pixel is divided into... Yep. Each area is divided into KXK. Oops. Is that right? It's me to mult or something. No, okay. The simplest. Is there a really? I do a multiply. Times, okay. Well, that's very British. X times X. Okay, back to this. Each area is divided into KXK grid, which I assume is, yeah. And sample, and a sample is drawn uniformly within each grid. Nice. Yeah. Oh, strata is multiple stratums. Got you. So I shouldn't say stratums. I should say strata. When I pluralize stratum. Also, yeah, 480p or bust, indeed. And they're upscaling as well, so it is just a tiny game. This is better than taking k squared random samples, since the sample locations are less likely to clump together. Here we will show why this technique reduces variance. I mean, you kind of just said so. This avoids clumping samples, yep, together. Okay, so we have a single stratum. Within a single stratum, the multicolor estimate. Yep. So Xij is the jth sample drawn on the density of pixels. The overall, okay. So this is pretty straightforward, but it's a, I'm gonna have to add a note here in graphs theory to reducing error in contour multicolor estimator. We can do this over a stratum. And that would be, open that up, and blah blah blah. Oh, it's not that one, it's I picked the wrong one, sorry. Not errors in multicolor, reducing errors, which would be this one. My mistake. Good job I checked. Right, so I'm just going to rob this latex so I don't have to type the whole thing out. Just add an extra few things. Lambda. Underscore I. And I'm gonna make this with our bar Monte Carlo estimator. Okay, so paste, and okay, so this is the estimating function, which you don't want. So go away, you, and you, and you. Okay, so this is I for each section, and I just got I. And then J instead of I. So this is just an inner for loop. Starting with I and J. Again, math people, I apologize, but that's how I understand this stuff. How do I do both? That's the question. Is that a thing? No. I think I just have to do this. Yeah. Where latex x underscore ij is within a nested for loop of for each stratum by pixel density pi. Nice. The overall estimate is of f is that, which is just where vi is the fractional volume. Sure. So if you add all the strata even. I'm trying to strata together, you get this, where F equals... hi Matt, good to see you, man. Well, I just met a machine learning professor and he's said I should learn more about Monte Carlo algorithm. Ah, I see. And you're showing it on stream. Yo, look at that. So the stars were aligned. Yes, this is all Monte Carlo stuff. And hello, yes, good to see you, my man. Yes, I don't exactly know how they use Monte Carlo, but I know you've been interested in ray tracing, and yes, this is all ray tracing adjacent. So yeah, that's kind of cool. F underscore I. Yeah, okay. Where Vi is a fractional volume of the fractional volume of stratum. It's the fractional volume of stratum I. Isn't that just like a... Yeah. I think this is just too complicated. So it's fractional volume. I don't need to define that so formally. It's just a part of... This is literally just... If this is a fractional volume, then it's just I over I. Is the ith fractional volume, right? What did they say about machine learning with Monte Carlo? How does that work? I'm kind of curious. The true values of the integrand in stratum. The true values of integrand in stratum I is... Okay, so the true value of the... This is actually quite understandable, to be honest. It's starting to make sense. So the true value of the true value of the integrand in stratum I, and then we just do the variance, which is basically, I believe, probably the same old as what we did earlier. So this is the true value, and then we got to figure out the variance based on the true value. I have a feeling that we're going to sample over it. Right, that's a Greek letter, I know that for sure. Let's see what the Greek letter is. It's a U looking thing. So it'll be a lowercase one. Mu. It's mu. Let's go back to here. Mu equals, sorry, mu underscore I equals E F X, so we randomly sample. So the expected value, put these together, IJ, is equal to frac 1 V underscore I, sorry, int, and then we want to do underscore this, and this will be the stratum itself, which is nice. Lambda lambda I. So we integrate over that and dx. So that'll be the that'll be the integrand. So the expected value of the function sampled over that, based on the stratum, is 1 over the fractional component of the fractional volume, integrated over the stratum for the integrand, which I believe is the rendering equation for that particular guy. So this is just splitting up the rendering equation into sections. So we do the rendering equation per group, rather than just for k squared, which would be the whole area. Assuming that everything's a square as well with k squared. So the variance, which would be the error value in the stratum, in this stratum, would be, and another Greek letter, which is which I'm not unfamiliar with. I always thought delta looks like a weird oil can or something. Anyway, what are you looking for? What is it? I missed it. O. It's like an O shape. Is it not? It's not delta. It can't be delta. It's not that, not that, not that. How am I missing it over and over again? V, T, tau. Oh, there it is. It's sigma. It's small sigma. Use a sigma mailing from me. Okay. Okay, so we have a squared. Let's do underscore first. I. Yes. I was worried then that wouldn't work. It's a frac. 1. Alright. And then V underscore I. And then int. And then let's say lambda. No. Underscore lambda I. Which feels, this feels very familiar to. Alright, so f of x minus the actual value squared. I wonder if we have to sample. I wonder if this variance is a sampled variance, or is it a real variance? We'll see. Mu underscore I. I'm learning on my Greek alphabet, I have to admit, which is a weird positive. Actually, I didn't expect to have to do. Anyway, all right. So, yeah. So, what this is doing here is we get the expected value if we do like a the expected value of f, and if we iterate over each, if we have a random number, then we iterate over each stratum, which is just a section of an image, and for each pixel. Then the expected value should come to something over 1 over vi, which is the fractional component, which tells us how much to split up the image, right? So if we have 20 regions, that would be like the 20th region, the 19th region, the 17th region. So 1 over whatever the region we're on. Then we sum up all the, what is it called? The pixels. We do the rendering equation, which will be f of x. We sum up whatever that will be for each thing per random sample, which would be, you know, which would be per pixel, but it'd be like per random sample. No, so it would be per pixel, sorry, which would be, that should be the x's, because that would be the value that comes out of here. And then we say, like, okay, so taking that value that we worked out here, it's just the same old value that we just worked out as squared. But I feel like that's too complicated to work out analytically. Thus, within the n underscore samples, the stratum in the variance, yeah. Thus, with n underscore samples, the stratum variance of the per stratum estimate is. This shows that the variance of the overall estimator is. Alright, I am ready to do some programming. I don't know about you guys. It's been fun doing this, but I also need to make sure that the quickness under my fingers, as someone said, doesn't start to get. I don't get to start legit get rusty because I've stopped. You know, I've started to stop code. So I'm going to change the music and because can I listen to something else? Some kind of like good sweeping soundtrack that I don't have to worry about would be nice. I can't put that on. That would be instant copyright stricken from the universe. No, we can't do movie soundtracks. It has to be video games. Someone is streaming. Who would stream? Jeez. Yeah, I could go back to that. I don't want to bore people with the same sounds. Let's go with the. Let's risk it with Baldur's Gate. I've never listened to this soundtrack. But we'll see how this goes. Hopefully it's good. If not, we'll change it. Alright, so goals of the stream. Coding wise. So the first thing I want to fix is this. It's pretty straightforward. I want to go full screen, right? Press the full screen button. It just crashes. Alright, so let's figure it's now become a crash button, which let's try and figure this out. I believe it's something to do with the refactor that we did, and I didn't test the resizing, which was kind of silly, but we'll have to see what it was. So the error was the allocator. Sorry, my hands are a bit. I want to change how I'm coding just for a minute because my keyboard is so low down. So if you bear with me just for a moment, I'm gonna grab. Oops, I think I just unplugged my keyboard. I'm just gonna elevate my keyboard on my hands. The problem is right now, I'm kind of typing on my knee, and it's not ideal. So, oops. So I'm just gonna grab something. So let's do a couple of pillows maybe. I don't know if hopefully you guys can hear me. But if not, I'll be back in a minute. I'm just on the other side of the room. Domain expansion crashed the program. Yeah, I think that's everyone's unfortunately default domain expansion. Let's see how this goes. So I've got two pillows here to elevate my hands a bit. So okay, so I'll try this for a bit, and if it's a bit rubbish then, because this isn't admittedly the most ideal setup, but it just made sense to be in this room today. Okay, right. What do we have? We have a crash. We try to initialize the buffer, and what ends up happening? We run out of memory or something? This is null. It's through an access violation. The address is really high. which suggests that we're trying to access something that doesn't exist. So I have a feeling that when we resize the swap chain, the temporary allocator, it doesn't exist. So we basically end up passing in a pointer to no, it does exist. Okay, so that, yeah, something's, it's like allocated but not initialized, if that makes sense. So what I'm going to try is just a cheeky rename, access, do it through the memory service. So memory. Yeah, it feels nice to code, I'm not going to lie, but at the same time I'm like itching to get on with that book, but I've got to not just do one thing the whole time. Because both, I feel like you can end up with coding as well, just end up not developing as a programmer because you only code under a particular... I don't know if that's true for, like, you guys. Yeah. There we go. So, it was just a crash button. Usually I crash the GPU instead. Yeah, I mean, just see the resizing. Yep, and the stupid one, which everyone, I don't think anyone will do, but the problem is it breaks the camera when you do that because it's not an aspect ratio that's like nice. So that's just honestly probably not going to be in the game. Or we shall see. All right, so that was fixed. What was the other thing I wanted to do today? Let's see. I want to try... Okay, so I was messing around with this yesterday, and let's get rid of this. Okay, to debug this, I'm in the mood for graphics, so I'm going to do bit graphics right now. As I probably, yeah, it probably makes sense because I've been reading a bunch of graphics stuff, but I want to improve the accuracy of my direction when it comes to what we're looking at when it comes to rendering. And to do that, I need to first get rid of the player camera. And yeah, sometimes you get in a rut where you're doing stuff you already know. Slash pretty trivial problems. Yeah. That's what I've been thinking about just then. I feel like it's the senior programmer trap that you can end up in. It's probably why, this is what I would guess, senior programmers, even when they become principal programmers, that's often just, from my experience, you're not necessarily a better programmer. You've just been at the company for a long time. But I feel like if they stop improving after a particular point because they just work on stuff they already can do, just in a company for 40 hours a week. Okay, so I'm just going to stop updating the player as well, so I don't have that flying around needlessly. But I might be unnecessary. I might be being unnecessary there. People might just, sorry, what I'm trying to say is people might disagree with that. Yeah, this isn't too bad, this music, I guess. Where is it? It's player update. I'm just going to look for that. Player dot update. Player. Oh, I casted everything. I remember now, yeah, because I started to move. I haven't quite finished this yet, so excuse the scruff nature of this. Oops. Let's copy, find, update. Ah, there it is. I want to get rid of the update. Yeah, so that won't be annoying anymore. So when we fly around, oh, nope. I've also got to fix something else. Okay, so visibility has been removed. Oh, I'm an idiot. Yep. I didn't uncomment stuff, but I also need to Do this. This is why this is here, just lag around. So the light is easy. Okay, so now we should have a free-floating camera that doesn't have any collision detection. Assuming that my shader is compiled correctly. I've uncommented my comment, which is not good. Alright, so let's just have a go. Once more time with feeling, eh? Alright, cool. So we're going to ignore that. My goal is more... So this is what I'm talking about. Like we lose... it's not quite right. So I'm going to try and figure out the direction at which you can see it more. I don't know if it makes sense to do it on the inside, but... So my position right now is a point camera, and we are not calculating the... I think it's the normals, but it could be the geometry. But I think the geometry is quite simple, but anyway. So we're going to tackle that right now and see if we can figure this out. And I think I'm going to use the filament library to kind of reference the actual implementation of what they did, just to make sure my normals are correct. So if you don't know what this is, library. Did I say library? I meant to say engine. They have a game engine, I believe, for Android. But it has physically based rendering, but it also has like a really nice... So this is what we looked at earlier when it came to that video. If you were here at lunchtime, we looked at the Ace Roller video, physically based rendering. And I am concerned that the way I think everything's correct. Like when I say everything's correct, like the Fresnel, all that kind of stuff's fine. It's just the direction at which we're looking at. Basically, we're getting the wrong vectors, and I think that's going to be a bit of a exploration today. Okay, so by the way, yeah, if people want this link, I can link it in the description, but it's in the description in the live stream chat. So yeah, I'm going to be looking at the specular, and first it might be a good idea to kind of like, I don't know, let me get some water. So what I've got to figure out is what vector does what, and then figure out what my vectors aren't doing. Maybe just output the normal vectors as colors for a real quick check. That's a good idea actually, but I wouldn't know which one to pick. Let's have a look. Okay, so here's... Like, let's start from the top, right? So we have the tangents, we have the bitangents, and where's our normal vector? Yeah, we shouldn't need to do this twice. This is kind of a waste. It's just a waste of computation, really. I don't know how free. It's probably almost completely free. But it normalizes doing something, right? Okay. So n. Okay, so that's the first thing sorted, I guess. So I might start renaming things. I don't really like the mathematical approach of just saying NV, because it doesn't really tell me anything. Yeah, I'm gonna. So that's the half vector, which I literally learned out yesterday. Which is L plus V apparently, which is the light is the going out vector, and the V is the going in vector. So our I is what we're looking at. That builds the view for us. So I might throw this into Paint just quickly, just so I can kind of figure this out. Say new. Alright, so I'm going to make this a bit smaller though, because I need to be able to reference this faster. So we have, let's do a white line. And yeah, hang on. No, actually, I'm not gonna. It's gonna take too long. Hello, Mado. How you doing, dude? Actually doing some coding today. Who would have thought? What the heck? The guy's doing what he said he was doing in the title of the stream. Okay, let's see. So, are these normalized? That's the first question. When... Because I believe these are normalized. There's an assumption. Oh yeah, okay, so normalize. Literally, it just says right there. I'm kind of interested to see the position. I'm just trying to fix my vectors when it comes to my physically based renderer. It's the BRDF part of it is busted, and I think it's the direction vectors. I don't think we changed anything. So if I go inside, it should be lit at all sides, but it's not. Although the vector is back, that's actually probably a bad idea to look inside, because the normal vectors are going to be completely backwards. But regardless, we're getting like, we should be complete darkness on the inside, I think. Yeah, but we're getting like super bright here, so I'd say the surface normals, I should check in Blender maybe the surface normals of these guys. Because if the surface normals are inverted for some reason in some random place, then it doesn't matter what we end up doing. Because that should be how it looks on the outside, but this is wrong. So let's just check this rock model, right? Because it's a very... I don't know how to do this very well, but well, we'll find out. But yeah, it's always good to check your models to make sure that the normal that you've got, the normals for your model, makes sense. Excuse me. So it's import. Okay, so assets. Out. This would be rock. Give it a second. Very nice. Okay, so now we need to figure out how to view the normals. Let's just Google it because it's going to be way faster than messing around with settings. How to view normals in Blender. So I'm just going to believe the AI on this because it's such a basic. So edit mode. So go to edit mode. Okay, Blender 2.0 is probably too old. Edit mode, view, viewport overlay. So where's edit mode? This might be the same thing I was just looking at. Oh, tab gets you into edit mode. Ah, there we go. Okay. And then what do we do after that? A viewport. Viewport. Where is that? Oh, okay. So it's this thing. Oops. Okay. And we want. Is there normals in here? Normals. Okay, yeah. Axis. Statistics, light, bones, motion. No, maybe it's this. This. Face orientation. Oh. Oops. Let's not do that again. Statistics. Okay. Light colors. No. Let's just go through the settings, I guess. Okay, so I don't want to watch a video, but I might have to just for this. It's going to be faster. Oh. Okay, so mesh, normals. How do I view that? Alt N? Okay. Alt N. Okay, so this is the normals. Yeah, let's just viewing normals. Oh, look at that frame rate rubbish. Or animation. Even. Okay, so let's type in how to view normals in Blender. Right. Right.
This is a video to show how to show normals and flip normals in Blender. In this tutorial, I will use the UV sphere. Go to Add, Mesh, and add the UV sphere. Close up
Okay.
it, and then I will go to Animal, and I want to delete the top part of the sphere. Go to Front Wheel, and switch to X-ray mode, and select the face, and select top of the face, and delete the faces. Then switch off the X-ray mode and change the angle. If you want to show the normals, we have two options. The first option, we can go to overlays and check the box face orientation. The blue color shows the faces are facing outwards. The red color shows the faces are facing inwards. The second way to show the normals, we can go to merge animal, click it. We can find the normals. We can check the box display face normal.
Okay.
We can adjust.
So that's what I actually wanted to see. So we were close, because it's just grey. It's red on this side, so it looks like it's correct, but and then yeah, no, it's all correct. These surface normals look good. That's what I wanted to see. Nothing stupid, nothing weird. Fantastic. Okay. Yeah, maybe they appear inside the mesh. I think it is red in here. But I don't. What I wanted to see is this, because I wanted to make sure that it makes some logical sense, if that makes sense. Like maybe they're facing the right way, but they're all facing down. You know, like they're all facing silly directions. But no. It's all so because that would make like weird effects in our case. Yes, face orientation is red and blue. Normals, lines. Yes, it all looks correct. Okay, so effectively we can blame ourselves now without worrying about the engine. Sorry, about worrying about the model. So we normalize the I minus the position, which I believe is correct, as far as I can tell, for one light anyway, because we're only doing this PBR for one light. That's why it's so fast. Hi. Not simple or unreal. Good to have you here. Hope you're having a great day, my guy. We are just doing some shader coding, so trying to debug an issue. Okay, so we have the TBN, which is tangents building up in a column, tangents, bitangents, and normals. How is the game going so far? Yeah, not bad. Mostly I've been educating myself on lighting recently so I can make this look nice, but we're trying to fix the lighting so it's not as bad as it currently is, which is show you, I guess, while we compile anyway. So ignore that, but yeah, what I'm trying to fix at the moment is how dark the scene is. And I'm trying to fix this, like looking at things from an angle makes things kind of look strange. So for this rock anyway, we're trying to get it to be uniformly lit from all sides. Yeah, so it's going good. Yeah, thanks for asking, by the way. Okay, so I wonder if we could just do the diffuse and non-specular, and so visibility and distribution. Like, what is the problem, do you think? All this is in Vulkan. Yes, this is all Vulkan. Vulkan renderer. Okay, so my sneaking suspicion is that. Okay, so we got distance. Why do we do this twice? Which is kind of suspicious. Because we have this for L, which is light minus position. And here we have basically light minus position twice. So we get the distance between the light and the position. Dang, all I've used is Raylib, which that's cool. Which is a simpler version of OpenGL. Yeah, it's a solid framework. It's actually really good piece of software. But yeah, I'm running raw, if that makes sense. just doing this all with Vulkan. No help. Okay, so I think I broke this at some point in the past. I don't know. So the denominator, what is that used? So the distribution. That is used for alpha squared. Okay, so this is for the, if I go back to here, This will be the normal distribution, which is probably where things are going wrong. It's like Python programming for graphics. Oh, really? Well, you can probably do a lot of good stuff with it. Okay, so... True, yeah. If you want to like design a game faster, it might be the smart approach. Rather than having to learn a bunch of graphics theory, you can actually, I don't know, maybe Ray Lib, you have to know a bunch of graphics theory. I could be wrong there. Okay, so let's see this denominator, which I kind of threw together at one point. So I'm gonna I wish I could comment this. So the way they do. Okay, so I'm just looking at their source code because this is the filament engine, which probably has an accurate physically based renderer. Vulkan is a 1,000 lines to draw triangle. Raylib is really, it's that simple. Oh wow, that's interesting. Yeah, it's tough to get started with Vulkan for sure, but it's fun. Okay, so its a value, which I believe is corresponding to these variables up here, as far as I can tell, is a squared, which is not roughness times roughness. That is roughness times nh, which is the normal vector dot half vector, which is interesting. But where's the a end up? Divided by roughness. Yeah, Madhu, I saw the struggles. I was really happy when you were able to render that triangle, and then later a cube. It was all good stuff. Okay, so if I take my roughness, multiply it by the normal and half vector, then right, so I'm gonna take this for inspiration and kind of see what I'm doing, and then kind of compare the two. So this is for, what is this for? This is for the entire GDX? Yeah, because I have more going on here. I have this kind of idea more than anything, which is the Smith's GDX corrected version, which is roughness x roughness. Yeah, I'm probably never going to learn anything past Raylib/OpenGL. Yeah, I mean, if it makes sense for you, that's 100% like a really good idea. Okay, so we have the normal vector versus the L, which the L, I believe, is the light, and the V is the visible. So that's what we're looking at, I think, if I look at my code. So yes, the V is visible, L is normal. So we have roughness times twice, then for GX, then we have the normal dot light. Okay, so let's have a look at our GDX. Okay, so we've got it backwards, which is fine. Let's rearrange these so it's easier to... I'm going to take their code and kind of work backwards. Yeah, you're not wrong there, Ratchet. I was obsessed with that for some reason. I remember like in video games I would call my character Vertex F, because I'd be like referencing OpenGL for some reason. I thought it was cool, although escape point's not much better, to be fair. The coolest username ever. Okay, so n.l I can use that, but I feel like, yeah, it's the bottom one. It's just faster but less accurate. So we, as far as I can tell, if I copy this down here, because I kind of already used it. I did see someone, I think it was Arsini's tutorial, when he does about meshlets. He has in the first or second video, in the second live stream, I believe, like he, or when he actually renders a triangle, he shows you how simple it was back in the day to render a triangle, and it's like literally 70 lines of code. It basically fits on the screen when you want to render a triangle in a Vulkan, OpenGL 1.1. Alright, so let's hello. Should I create my own graphics API? That is up to you. If you're interested in driver development, like learning how drivers work, it'll be written in assembly. It will have to be written in assembly if you do that. But honestly, I don't know if you're joking there, but I'm going to pretend you're not, just for this sake, and say that if you are wanting to get into driver development, where you write your own like working it in NVIDIA, that's kind of like what they do. But you will have to know so much when it comes to computer science and stuff like that. So it'll be a severe undertaking, as far as I can tell. Okay, so sorry, I'm looking that over and over again. Don't need to do that. Huh. So they do. So I don't think I've ever got this right. This is actually just completely wrong on my end, as far as I can tell. Ah, man. So I'm just going to do the simpler one right now. The simpler G part of the BRDF. The specular. So it looks like we should do this. I'm going to read some documentation after. This should be L for the light. So the normal dot light, normal dot L plus, and then that is 1 over the visibility. And then the specular BRDF is multiplied by, and I think I'm using the simplest diffuse of all time, but I do mix them together with the Fresnel, sorry. Let's see how that looks. So yeah, ignore the duck. The duck doesn't really have any interesting normals. So I'm going to stay away from this rock because sometimes the geometry gets really... No, it's still being weird. Yeah, because when I go down here, maybe... Oh, it's lit a little bit more correct, I think, but... You see, this is not what I'm after. And if I go inside, which... Because the normals should be backwards. Yeah. Okay. Oh, my laptop's dying. Don't want to lose you guys. I can't talk. Yeah, I think something is flipped. Yeah, I think that's what it feels like, doesn't it? It feels like there's a vector that we're just not correctly getting right. So, and I'm just trying to figure out exactly if I got rid of this. Yeah, let's get rid of the not the specular. Yeah, I just want diffuse, right? Based on the direction. Because it could be. If I get let's get rid of. Let's see. Let's get rid of. Okay, let's work backwards. Let's get rid of the emission, right? Yeah, I don't exactly know. We're gonna have to narrow it down there, Ratchet. That's my problem at the moment. I don't know what I'm missing. So it could be. I'm just gonna work backwards, making sure that nothing is gonna work. I'm gonna remove basically stuff. I'm gonna remove when we mix the fernal and the conductor fernal and the metalness, we're gonna move backwards and just see with diffuse lighting exclusively, do we get the same kind of weird lighting normal thing going the wrong way? So I don't think the emission's going to do anything because I don't think it has an emission anyway, because I don't think it's a light source. It's technically, I've made it more correct, but it's just not, it's not lit properly, like up here. You know what I mean? Like, if I'm looking at this should be lit here where my mouse is. So, Mado said, an offset of the source light might maybe moved or something like that. I feel that's what's happening. An offset of the light maybe is moved. Was just gonna say it's slightly better, yeah. An offset. I don't think it's more likely that. Okay, let's do another thing as well. Let's remove the clamp. I don't know what this is either, and why I did this. Is this to normalize it? This would be the angle. Why am I adding a random, really small value, an epsilon? So this is the angle between the two planes. If I don't get this right, with the visible and the normal, then it won't accurately describe the direction of what we're looking at. So let's see this how this epsilon. I think this might be for whoops, I didn't want to do that. I'll do it like this then. I think that might be for floating point precision. But I'm just going to make sure that epsilon isn't causing anything. So that really shouldn't make a difference, but or a large difference at least anyway. Yeah, it's I don't think a large difference has happened. But maybe it has. Go inside. Yeah. Now, I'm just going to have to assume if it's not correct, I haven't solved it. Nothing. Oops. Unless it's like massively visually different. You've kind of inlined every function into one big function, so it's hard for me to read the BRDF. Okay, let's you're right. Let's simplify this a bit. Okay, so the GDX, we can at least easily split this up. So Yeah, so this returns a float, I think. We'll have to see. So this returns. Yep. Let's do Smith. Okay, so this takes in Vec. Is it? What are these all called? These are dot products. That's a float. N dot V. Yeah, I think this is going to help me debug things as well. Okay, N dot L. So there's the two normals, I believe, and alpha squared. Let me just grab this. Oops, need to make it a float. Okay, alpha squared, NDL. Okay, so I'm going to throw this in at... Let's call this G, I guess? I don't know. So we're going to get rid of this. So we need V. Yeah, this is going to take a minute, guys. I apologize. We'll see how far we can get. My hands are legit sore from using this keyboard in this position. Ugh. Let's try. Oops. It's not. It's like the top of my hands are sore for some reason. Whew. It's not like I've been typing a lot at all. It's I think it's just the position I have my hands in. Anyway. If David Goggins can run a few miles, then I should be able to do this. Anyway, okay, so float G. Do it like this. Time to get the 1K split. Ergo. Is that some David Goggins law or something? 1 split, ergo KB. I'm sure that's some madness that I don't know about. Okay, so this is... Oh, is this the default? Alright, let me just look at the BRDF properly. No. This. Okay, so this is real-time constants BGF. DGF, sorry. So, oh, split economic keyboard. There we go. Yeah, oh, is it what? Is that how much they cost? Jeez. Yeah, no, thank you. No, it's just I'm in a scuffed setup because I wanted to stream longer, but so the normal. Okay, so this is the D, so I should call this the D, I guess. And we'll just kind of reconstruct this based on these functions. And we'll try and hopefully get like a BRDF that makes sense. I'm just going to skip everything. What I'm looking for is just when I did X, Y, and Z, if you know what I'm saying. I didn't do the first one, I don't think. Okay, so I've got D and G mixed up. Okay, that was originally G. Okay. Confused, but now not. Okay, so the D, which needs to be at the top. This is where you take the roughness. Let me turn my microphone a bit. And okay, so roughness times by dot normal vector half. So I must have that somewhere. So I'm going to get rid of these two for a minute. Where do I do that? So light intensity. Yeah, so there's alpha, which is hopefully roughness. Yes. Okay, so where is that code? Yeah, admittedly this is very confusing for me. Now I've come up. I typed this out once and then kind of went, alright, it's done. That was a bad idea. I'm just going to absolutely make sure these are different. Okay, yeah, they are. Yeah, so I just need to get the D, which is alpha squared so no, what I've done here is that they're all the same. Let me look at the maths. Yes, where's the equation below? We need the Cook torrents thing. Okay, so the DH and then Fennel. And then we have the whole thing. Okay, so let's break this down. They are definitely different, but they are very similar. Alright, let's just grab this, right? We can write this in our own code. And just work it out, right? I'm not going to call it that, but I don't know what this is called, to be honest, but oh, I didn't return. That should be return visibility. Okay, so we got roughness. So we centered the roughness and the, I think I called it dot, didn't I? I didn't like this. Dots. What's K? Yeah, roughness is fine. And we're going to take this. I'm going to call it something that makes sense. What is this called? The specular. No, the normal distribution function. So the what is visibility? It's just the final division that you need for that GDR Smith thing. So the normal, but this might be the error. Normal distribution function. Alright, so take this out, and that'll be the D. Float D equals this, and this takes in the N dot H and roughness. Okay, so now we need the Fernal, which is worked out with all this stuff. Okay, so take this. Put this in the Fernal. I'm just going to call it Fernals. Or Fennel, sorry. The Fennel. Let's call it the right name. Fennel. And throw this in here. This returns a vector, it looks like. Let's see what you return. Blah blah blah. Yeah, vec3. Vec3 is vec3. Vec3. And the Fennel. Okay, so okay, so when combining two things together, it looks like. So I'm actually... Did I cut this out? I probably don't want to cut that out. I'm just going to comment this out. Instead of cutting it. Sorry, excuse me. Because it's using some kind of other bit of maths. That may be wrong, but I just kind of don't want to lose it. Maybe make a new shader, who knows. Fennel. So let's see here. To do the Fennel properly. I am just going to take the slick with 0.4. Okay, so I think in my code, if I paste it in, the Fennel thingy is... Oh, yes, needs to be a vector 3. Is that. And it takes in the... So that's the slick. Okay, so we have a second function here. We do that. Yeah. Okay, so let's do the... Let's split this up again. The Fennel. And, oops. Put this here. Yeah. Right. Okay, so... I'm not going to call it that. This is a F0U. I think we only need F0. Shouldn't you use roughness in that equation? Sorry, what equation? I don't think I need this variable. And then return FR. Sorry if I've missed it. I kind of went through it. There's roughness here. But this the final Fennel thing, I just need to... Why are you... oh, it's a float, yes. And... He has done this properly, and I've just faked it. Hang on. Hi, Kalia. Yeah, it's going. That is supposed to be this function. Sorry, yes, and I do that in the alpha squared is the thing that I pass in is just that is the roughness squared. And you can see that here. I just pass in the alpha instead. Yeah, I'm just I hope you're having a great day, dude. I am refactoring my what is it called? My fragment shader, because it's kind of scuffed when it comes to its lighting, so we shall get this to be better soon. Okay, what have we got? Give me a sec, my hands are... It is a little bit hot. Where is it? How hot is it where you are? Is it, I hope it's not like above 30 degrees. Because that's where I start suffering really, really badly with heat. Okay, so we have A, which is not good. Okay, so for the normal distribution, we need to work. Okay, so okay, cool. Normal distribution function. We have the corrected. Blah de blah. We have 26 is still pretty tough. Yeah, 26 is like, but 30. Ugh, that's where it gets miserable. Yeah, I don't like it at 26 either, to be honest. I'm okay, so let's work this out. How do we... Okay, so F... This code is so different. But it looks the same. I thought it was the same. Hang on. F plus 0 times by... Right, let's just stop minimizing this stuff. That's hard to... It's not good for the viewer. Sorry about that. It's 49 degrees where you are, Maddo. Oh my goodness. Oh no. I hope it cools down. That sounds horrible. Today's 26. I like rain in summer. Yeah, totally. I agree. People moan. It's like, oh, if it was only sunny all the time. But then it gets like really, the air gets really. Blech. Anyway, okay, so. Yeah, I couldn't live in those countries, those Arabic countries. Oh yeah, you actually told me where you lived a long time. Well, where you're stationed at, where you live, whatever. I think it's kind of cool. Got people from all around coming in. yeah. Maddo's living in volcanoes. See you, Matt. Appreciate you, dude. Thanks for turning up and checking us out for a bit. Yeah, have a good night's sleep, man. Well, I assume you're going to sleep. You said nice. Yeah. It's fine, he says in a panicked voice. But I guess you get used to it. I don't know. It's anyway. Let's I've got to concentrate. Won't be harder than Vulkan. Yes, that's it. John Vulkan lives in the center of the earth. That's how hot he is. Doesn't even break a sweat. Anyway, I am struggling to understand this. All right. Let me move my mouse pad one moment. Sorry about that. Of course, it's on 24/7. Yeah, I'd be taking that thing, the air conditioner, with me. I know it doesn't work like this, but I would try and make it work like this. I would take it with me wherever it went. Even in the bath. Yeah, 2023. I remember that being horrible. It got to 36 in the UK, and that's pretty extreme. I feel like I want to rewrite this whole thing, honestly. It's just so confusing. Like, I've got part of it written. I feel like it's doing stuff, but it's like mixing all the components together. I think it's confusing me is like the specular and diffuse BRDF, which are only like parts of the function, are getting like mixed with the conduction Fresnel, and then get mixing again, then get mixed together with the slick. I keep calling it slick. It's schlick. Fresnel code afterwards. So what I think is like we like multiply half the equation together and then do some weird multiplication, and then we have this denominator here, which is like, I think that's the bottom half of the equation, but I can't tell. This is always the correct move, just deleting stuff from scratch. The problem is I wouldn't really know how to fix it yet, because I haven't delved into the... yeah, because I've been reading this book, obviously, right? And so far, we've only talked about, basically, in detail, the Monte Carlo part of the ray tracing algorithm. But the whole point is so I can do stuff like this easier. Fenix, yeah, that's an interesting way of saying it, I guess. But oh, give me a, it's getting my hands a rest. Oh. Just can't get comfortable in my hands. Ooh. Maybe I should start coding with an Xbox controller. Yeah. Industries went crazy in production after COVID-19 is the reason why it was so... Oh, interesting. Huh. Never thought that, yeah. The excess fumes in the air. Okay, so I'm going to do this a bit different. Let me rearrange myself and before I throw the microphone on the floor. Hopefully I'm not coming across as complaining. I'm trying to get comfortable, that's all. I'm Morning, Mika. I hope you had a good night's sleep. Yeah, it's oh dear. I might need a good night's sleep soon. Who knows? Right, so let me fix a couple of things as I rearrange. Okay, so I'm going to try this. Hopefully you guys can still hear me. If not, let me know and I'll just speak up. But yeah, I'm going to try a different position. Alright, cool. This will do for now. I'm less at a right angle when it comes to my keyboard and mouse. Okay, so we have this, which is pretty standard. We have this, and we need the equivalent of. All right, so let's just do what they're doing instead completely. Yeah, and ignore what I've done. I'll comment it all out. So let's make a new main function, I think. Void main. And what I'm going to do is paste all the same thing in here, but I'm going to have full rights to delete everything in. So I'm going to restore all the code in here just before we continue. as if it was untouched. So I'm gonna put this back. This, remove this. As far as I can tell, it's basically what it was. Why is this? Oh yeah, I swapped them around. Let's bring them back. So I'm just going to do this. Get rid of there. I want as many things unchanged in this function as possible, so I can beat up another function. And there's some commented out code which I deleted, which I'm going to bring back actually. You woke up an hour ago, still sleepy. NVim action. Not entirely sure what that means. You're talking about NeoVim? NeoVim action. Yeah, this feels better actually, like almost like lying down typing. Alright, and pretty much done. Okay, so that's fine. I'm going to leave that the same. That's just a mild improvement. So now I'm just going to comment out this main function completely, and we're going to try and write it in the way. Okay, so we have this twice. So now we can beat this up without any issue. So what I'm going to do is just delete all this. All I'm interested in is the BRDF. Let me get rid of this. And in fact, what I could do is this is what I full implementation. Okay, so let's improve BRDF. So yes. So what I'm going to do is, I don't recommend doing this ever, by the way. Don't do what I'm about to do, but what I want to do is just copy this all out and kind of make my version. Yeah, like don't do this. US restricted Fable 5 and Mythos models. I see people dependent on AI. Yeah, it's, well, you know, it is. So what I'm interested in is not wiping out anything that I've done. So basically, emissive, that's fine. I want to keep all this, distance and intensity. And what we're going to do is, don't do that. Oh, yeah. Oh, okay. No, this is already. So I'm going to do this. Don't do this. This. What I'm going to do here is I'm going to why I'm saying don't do this is just because it leads to bad habits, copying and pasting code, in my opinion. You may disagree and be like, it's completely fine to copy and paste code around, but it shows it's like not very disciplined as a programmer to do. Why I'm doing this is I just want to see it work, and then I want to work backwards from that, and then like integrate what I need to integrate into this, if that makes sense. So yeah, don't do what I'm doing here. This is not a good thing to do, like I said, in my opinion. Because I've personally, maybe people are talented enough to be able to get away with just copying and pasting code, but for me, oops, yeah, this is fine. I've struggled to fix things after a particular point. Okay, so L. Right, I'm just gonna have to go through this and just kind of capitalize everything. Oops. What was this? Yeah, it was H. Okay, so I think it's the same anyway. No, they have different. Okay. So we're gonna have H. Okay, and then we have the light intensity here. Learning by yourself is better than AI. I think so. I think so. I think, like I've said, if you use AI to especially write your code for you, you end up falling into the trap of your skills degrade, even if the product you make is better. And that is not a trade-off I'm willing to take, personally. Okay, so this is the diffuse BRDF, this is the specular BRDF. When I combine them, which I think I just need to not literally delete everything, I want to do... So I have the Fernal mix, and if I take the intensity like this, I think we should be good. And then just throw that into... so intensity times by the Fernal mix, which is the... I think I don't need to do this. I need FR and FD. What if you don't have skills in the first place? Yeah, that's a good point. It's a tricky one. I think developing skills should be your main priority, but I know you meant that as a joke, but it is good to think about these things every now and again. So yes, so this is taken from that, which I don't really like. Okay, so distribution, denom, and alpha I don't think I used. We have light range, we have the intensity. Okay, so now we need to mix these colors together. So your specular and diffuse. Okay, let's just see what diffuse looks like. So what I'm going to do is multiply this by intensity after... Can you do 1 like this? Actually, you know what I'm going to do is put them both in here. By the metalness, and then... Oh, yeah, okay. At work I rarely work with my own code, especially if it is the same as working with copy and paste code. But I agree, it's easier to understand your own code. Yeah. No, I wasn't joking. If a coder wants assets for his game and he isn't an artist, can he use AI? Okay, so you got to be careful with programmer. What I would recommend, honestly, this is the way I'm taking it. Is I am almost using not bad assets, but you know I've got a duck, right? For a player, that's deliberate. I'm using bad art on purpose to signal to people that this isn't the final artwork. If you want to make art asset, I feel like from my personal opinion, again, this is just opinion. gamers in general would prefer to see bad art made by you than AI art that's air quotes good. That may be a controversial take there, but yeah, I really do think that's the case. When we do this summarize, do we apply lighting? Is there more? Oh, I see. It's got the clear coat on. But that's hard for me to say, right? I can't. If you when it comes to AI, I don't know. I don't know. In an ideal world, you could pay for an artist to make the art for you, but we're not in an ideal world. I understand. It's difficult for people to, and I don't want to be the guy who says that you should do this or that when I'm, one, haven't done it myself, and two, you know, might be in a better situation that I can actually do that. It's not. But that's just the vibe I get from people. Is AI art. By the general vibe is that they would rather see bad art than AI art. That's just the general vibe. They want to see you genuinely. They want to see you as the creator through the art that you've made, which includes the game itself as well. I use AI, but not copy and paste. Rather as an efficient way to gather information. Use AI as a search engine. MS Shadow. Also generate code. The only reason I don't say generate code is I'm assuming that the person who's wanting to do this wants to become a good programmer and isn't that concerned with the outcome of their efforts yet until they get really good. But that's, I don't know. Some people are different than me, and I understand, like, they just want to get something out there. I use a search engine rather than having to search the web for stuff. Yes, that's a good way of doing it. I've found that when I've asked AI something, I just go to the sources that it's provided rather than listening to what it had to say about the sources. Oh, so you said, if an artist wants to make a game, is he allowed to use AI? I think it's up to the person, honestly. The vibe that I get is art assets themselves are less popular by a large margin than using AI code when it comes to the general population when they talk about AI. That's all I'm saying. Yeah. Yeah, exactly. So it's a different, like, people see code as like something that's in the way of a product that's trying to be released rather than a craft that needs to be developed over time. So I can totally see that people are like, Lambert, okay, what do we do after the apply lighting bit? Alright, let's FD. Oh, I feel like I'm just not skilled enough to do this, like, especially now because I'm getting tired. And I don't want to have to read all this to understand it, to be honest. Because assuming that it's not that I don't think it's working or anything. It's yeah. Yeah, I'm getting a bit tired. But for me, it's like I would like to I would like my engine and my game engine, all my coding ability and stuff. What I'm looking for is just like the solution here. I would like to provide that. I would like to provide the ability for artists and maybe even designers to work with me in my game. Maybe this is just a bit of a thing, but yeah, I don't know. Maybe I should be quiet about this. It's like I don't think it's like I can't talk about. I'm just getting tired, so my opinions are getting sloppy, and my thought is getting a bit weak. But generally, I want an artist slash musician slash person to work with me, and then I make their art slash thing as good as it possibly can get. Like so it's one of those things where it's like I don't know about AI, and when it comes to that, I would rather them not have to vibe code and make something sick with me, you know. But anyway, that's no, I don't think there's anything here that we can use. Yeah, I'm sorry, I'm just getting a bit sleepy, a bit tired. So my conversation on this is getting a bit weak. So I'm just gonna move on from the AI topic. Hopefully that's fine. You can obviously talk about it amongst yourselves, but just don't argue, and everything's chill. I just can't give an opinion. I just can't give a well-formed opinion right now. That's all. You could probably understand what I'm saying. Yeah. Let's just go to the bottom, see what's at the bottom. This is like more substantial than I realized. Right, let's just see what happens. So I'm just gonna return there's gonna be low material. No. I'm not even going to convert. No, we can encode this back out. Let's just take the last line of code in here. It's simple. Frag color even. Alright. So pair pixel fragment. We still have base color, right? Yeah, okay, so 148. Okay, yeah, so let's get rid of these for a minute. Okay, so build error 300 expected right brace 306. Okay, go down. Oh, I didn't see that. Okay. Redefinition of H. 399. Normalize. Where is this? That it's here twice, right? Yeah. Alright. Perpetual roughness, where's that used? Oops, nope. Okay, so I'm looking for this guy. Perpetual roughness. Okay, so that is not what I expected. That is just literally roughness. So let's so roughness is equal to roughness times roughness, and then squared. So I'm going to put an S here for squared. Let's put squared. Let's not be lazy. And let's see. F0 is undefined in 409. F0. So in the so what else we got here? We got, is that the only thing that's undefined? I think so. I'm going to say 0.04, I think. Yeah, 6 hours. It's a bit of a stretch. No matching overload function. Oh. Oops. Almost 7. Yep, we're going for the full till 5 o'clock. I hope people have enjoyed the longer live streams. I think I've been quite worried about them, to be honest. I've been thinking about like, oh, maybe I'm spamming everyone with content. So I really hope that you guys have been enjoying the longer content, because I've been enjoying making them. You could be close to 12 in the past. Yeah, it was yeah, exactly. So it's so yeah, I've very much enjoyed hanging out with you guys and reading like a book that's like stretching my ability. I feel like I'm getting better as a programmer, and that's the main reason I'm doing this. So, but I hope you're enjoying the journey. And the reason I was worried, I didn't want to spam my YouTube channel to death, and then everyone gets like, ugh, this guy just makes low quality content type deal, you know. Keep them coming. Love that, Madhu. I take my time with 6-7 hours in C++. Yo, that's really good. That's like really solid hours, especially. You'll get really good, in my opinion. I've noticed I've improved. I've been trying to find a live coding stream like this in general, although this level of coding is above my level. MS Shadow. I appreciate that, guys. I appreciate you all. It's because the last thing I want to do is well, the most important thing is become a better programmer. That's why I'm doing this in the first place. But also outside of that, if I'm the last thing I want to do is, you know, put you guys off in the long run, you know, because you know, I very much appreciate you all, and I'm very grateful that you're here. So I don't want to, you know, feel like I'm wasting your time. So yeah, I'm glad that, you know, you guys are around for that, which is, you know, very much appreciated. One tip: never use functions in C++. never use functions in a function in C++. Good. No, that sounds like a forward. Yeah, you got to be careful with the. I would look into C++ most vexing parse. I don't know if you've come across that. You may have in the book, the Strawstrom book that you read, but it's a good one to check out, because that's kind of related to having a function within a function. C++ most vexing parse. Check the Discord for the results on your long streams. And yeah, it's definitely worth looking into if you've never seen this before. I would say functions within functions are fine if they're lambdas, but like a full, I don't even know what that would look like, to be honest. Lambdas are fantastic. Sometimes local functions can be nice. Yeah, I think Callie is talking about like literally writing another function like f double in a function. So check the Discord for the results of your long streams and our talk earlier. Oh yeah, okay, yeah. will do. Thank you, Mado, on that one. Yes, you know about lambdas. You can't define one without a lambda in C++. Yes. Yeah, I've never... Some weird syntax, like, can you do this weird thing in C++? A lot of it's like, I don't even know how you would even do that in C++. What would this F0 be? Let's actually try and use my brain for 5 seconds. And the F0... What would it be? Okay, just skimming reading. However, looking further on the distance. Raise, yep. Inflection of index, materials, F0. The amount of light reflected back is noted by F0 and can be derived from the instance of reflection as well as section. So let's have a look. The instance of reflection. Instance of reflection. So the instance, the Fresnel term F0 specular reflection is a normal. Instance angle is achromatic for dialectics. We will use the remapping of dialectic service in this thing. The goal is to map F0 onto a range that can represent the Fresnel values of both common dialectics and surface radiance. Okay. So when we're working this out, how do we work it out? You're on chapter 7 of this book. Nice. Yes, Strawstrom's. Yes. Why? Technicalities, functions. Ah, you're on functions. Hell yeah. Why do you have a Fresnel effect in space? Just to be physically accurate. It's not always about water. It's about the. Oh, I could give you a better. It's about. Let me think. I just. Because it's like everything has a Fresnel reflectance, which is dependent on common is like the reflectance like parameter. Like you need to kind of maybe I could just pull this out. Yeah. No, I should really try. It's in my code. Let's just look at my code. How do I work out the 0? Float. Yeah, I just say it's 0.4 because I just say it's the normal. But I don't know how to denote a vector, which is kind of difficult to figure out. Like, what should be that value? That's why I put 0.4 earlier, because I was like, oh, it's just the 0.4 value, but it's for some reason a vector. Let's look at the function, right? So it's the plus. So in my code, I have the same setup. And he is taking the. Did you fix the lighting issues? No, I'm kind of rewriting my whole shader. So not yet. Let's see if we can get this done before I end. Let's see. Okay, so let's see. So we have the vec3. Oh man, I wish there's a way to not be tired. Okay. So that, what is that returning? That's mixing both. Oh, I see. Okay. So when we multiply these together, it's doing that here. Well, I'm doing it here as well, but I don't think that's fine. I think. Let's just see what things look like without the fennel in it. Whoops. I'm kind of curious to see like how, without that part of the BRDF, then maybe V is redefined. Oh. I'll just type V. Just for now, because I'm just interested in seeing this. 13. We have what's. Oh, I see. This needs to be a vector, right? Okay. This needs to exist. So if we take. I do not understand what that's going to be then. It's the I incidence of reflection value. It's the incidence of reflection. Okay, so we have the mapping here. Incidence of reflection, incidence of reflection. Okay, so is there like a base? Okay. Okay, so it's just base color times. Okay, that's all I needed to know. Found it, found it, found it. Okay, finally. So we just take the base color, which I do have, multiplied by the metallic value. Meaning that we likely don't need to do any of this down here. We just need to kind of like, I believe that. We'll see if mix works, but I doubt it will. Oh, we need to times by F. Ugh. Okay, so let's build. Okay, so I don't. Okay, so this is a Vec 4, I think, because base color is a Vec 4. So this is color is F0. Vec 3 equals this times by Vec 3. Oops, no. Okay, equals. Then RGB. Okay, so that will give us the vector that we're interested in. So I'm trying to overload it with a value that makes no sense. I assume you've already. I could maybe have a material anthrotropic fennel. Cobain's amount of coffee works for me. Yeah, that's a good way of. That's a good way of staying up. I assume you have seen it already, but filament has a full BRDF. In GLSL. Yes. We're kind of robbing that at the moment. We're going to work backwards once it works. We're just running into shader compilation issues, and then we'll just see. This would be, why did I call that? This is what is this supposed to be? I assume that is the diffuse color. Where's that come from? I saw you copying from individual functions, so I though maybe didn't. I know, sorry Ratchet, I know it's this is okay, so that's what that is. I'm kind of just making sure I wanna have a complete solution that'll eventually walk back and do it properly. It's not ideal what I'm doing, admittedly. Let's just make sure diffuse color is it undefined? No, it's not my best hour trying to do this, but I'm running out of time. I'm just trying to get it in. Where's the fennel thing that I worked out earlier? Metalness. Base color bias. Okay. Base color. Oh, U. Base color undefined. Shouldn't be. And U here. Is there any other colors that are wrong? Right. Okay. So. Okay. No matching for mix. Okay, so if I take the intensity multiplied by the direction, let's take these, multiply these together, but not do that, kind of like this, and we should maybe, O, and T. Right, you ready to see blinding, terrible lighting? Oh my goodness, we actually have lighting. Like, I did not expect that. That is surprising. It's super dark though. Oh, you know why? I'm not converting to. I am converting to HDR. I mean, load LDR. Huh. Yeah, it's. I think it's. The angle is correct. Yeah, thank you. That is kind of what I'm going for. It just almost feels like it's too small, the light, when I go around these rocks. You know? Oops. Yeah, it's like the intensity is tiny. It's like a tiny little point light. The point... Yeah. I think it might be working. Despite, it's just really small. Okay. Right. Okay, so we have a accurate BRDF. The lighting is pretty lame, but well, I mean, it's just really dull. You can see it better on the docks for sure. Maybe. Maybe not. Let's see what the difference is. I see. Okay, so this. I think I know what's going wrong. That's giving me at least an indication. Okay, I think I know what's. Yeah, I think I know what's going wrong. But I'm gonna have to call it here, gang. It is past 5 o'clock. I hope you've all had a great stream. I know I have. This weekend has been a lot more fun. The fact that I could stream for such a long time and hang out with you guys. I will share my Discord if you are interested in joining. Yeah, I just want to say thank you for all your support and funny comments and great conversations. I honestly appreciate you all. And I'm glad you're enjoying these streams. It's given me a lot more confidence to keep on going. Yeah, I'll work on this off stream. Yeah, thank you all for all the help. And I will... see you all soon, and good luck with all your projects, and thank you for anyone who's liked and subscribed, and I will see you later. All right, bye guys, bye.